Welcome everyone to the Biomorphic Networks V1.0 webinar. If you are here, great. Hopefully you're not in the wrong place. So in this webinar today with Mădălin Gheorghe, I don't know how to pronounce your name. If you want to correct me, I always mess it up. These names, so he'll be teaching about a basically slime molds and swarms with his own custom plugin he's written for this webinar called Nuclei. You've all gotten a link to that in email, and I've also posted it as the first post in the chat, a link to the support webinar files. Biomorphic Networks is inspired by our master's degree program, Chapter 5, Cosmogony. Just keep in mind that this is a 5-hour webinar. That's a 9-month master's, right? So that's a big difference in the amount of content and education. But these webinars are existing to give you just a tiny, tiny taste of our professors and kind of the chapters and ideology going with this. Cosmogony is, in this case, at the larger city planning scale. This webinar will consist of mainly the Rhino software and plugins, so you shouldn't need any other software outside of Rhino, Grasshopper, and the plugins we've listed, as well as Mădălin's plugins. And Mădălin is a member of Zymorphine. Has done many webinars and workshops with us, and he's also the founder of his company Drag and Drop, which I believe he's at right now in his space, which is specializing in all kinds of new fabrication, primarily in 3D printing with different kinds of filaments and clays. I definitely suggest you check out his website. Some really amazing lamps and other household items. So I'll just quickly go to our master's degree here. So if you haven't seen on our website in Educations, there's our master's degree. It's a fully accredited master's degree, which lasts 9 months. Mădălin is one of the tutors among many other amazing colleagues from all kinds of different backgrounds and offices. And this, as I mentioned before, is based on the Cosmogony chapter, which is taught by Mădălin and also Desh, who is another Grasshopper guru. Definitely check that out. I don't want to waste time reading about it. Text there. Want to let Mădălin get to his teaching. Before I hand it over to Mădălin, just a few other things. We've sent you an email, so please make sure you read that email. The recording of this webinar will be available for 30 days, and you will receive access to it after the webinar once Zoom has finished processing. You will also get an email about a certificate. I want to remind you that you can tag us on Instagram if you would want us to see and reshare your stories at Zymorphine, and you can also tag Mădălin. When he comes on, he can let you know the preferred tag. I think you have 2, so I'll let him tell you that. And also at the end, whatever work you complete from this webinar, if you would like it to be featured on our website, please send them to results@zymorphine.com, any screenshots or final images, and we will have that email is also in the email I sent you, and it'll be in the following emails as well. So without further ado, I'm going to hand it over to Mădălin to start his webinar. Thank you.
Hello, everyone. Can you hear me all right?
Yep, we hear you.
Okay, good. Cool. So thanks for joining the webinar, guys. I am very pleased that you find this this topic interesting. So before we start, I just wanted to tell you that you should be aware of the fact that we have this Dropbox where we will be sharing the definitions as we go. So we will create the definitions in Grasshopper, and then we will upload them here where you can have them. So in case you are behind, you can always just open the definition, or you will have them later as well, just to you know, to have a second look. Okay, so we will be talking about the Nuclei plugin, which is based on the slime mold organism. In the Dropbox folder, I've also shared some interesting videos that talk about the recent surge in interest for this organism, and why scientists and researchers from all over the world are into it. So basically, slime mold is a unicellular organism. Even though it can reach like 0.5 meter in size, it's one cell, and it has multiple nuclei. That's why the name as well for the plugin. And scientists are intrigued by it because even though it doesn't have any brain, it's an organism that can produce optimized networks of transport. So the way it works, it maps the you know, the space where it's in, and then it creates some networks of transport for efficiently transporting food from where it finds it to all over its body. So people have been using it for urban design, but as well as like solving mazes, or some people actually, which I find like really intriguing, have used the algorithm to look at how the pattern, like how these pattern formations are. They kind of resemble the way the universe is formed, apparently, which is quite interesting. So you can find like more information about the organism itself here. Of course, we are not like, this is an algorithm, so it's an abstractization of the organism. So don't expect it to be 100% like in real life, but it is resembling the real life. And what's more interesting than just mimicking what it can do in the real life, it's also interesting that we can create environments and behaviors that go beyond what the organism itself can do. Another thing that's quite interesting is the fact that this kind of organism, it doesn't have a brain. It can solve complex problems, and it's unicellular. And if you think about it, like life at the beginning on Earth became as one cell, and by studying this kind of organism, we can actually tap into the origin of intelligence, and how intelligence developed. Also, we my personal view of this is that we've been, you know, romantically in love with ourselves and thinking that we are the most intelligent creatures, and maybe we are, but there are many other kinds of intelligence, and it is all around us. And by looking at nature and how other things solve problems, we can, you know, develop our own way of seeing things, and possibly look at things without you know, the human perspective that sometimes can be very subjective. The logics for the algorithms are have been developed by a guy called Jeff Jones in around 2010, 2011, and I've attached a paper in the folder as well. And there in the paper, you can see how different, you know, what kind of behaviors, what kind of ranges of behaviors it can achieve. Of course, we will talk about them a lot here during the webinar, but it's like, even though it has some simple rules that I will go through in a moment, it can produce like a multitude of effects and behaviors, and it's you know, it's very unpredictable. So like, even for me, like, I've written the plugin and I've been working with it for almost 2 months now, and it still produces a lot of surprises, and I'm still discovering new things, which, you know, I find really exciting, because if it was like something that we would it wouldn't produce any surprises, then it would be just you know, something boring. But this is something that it's almost like an alive organism. So it's really exciting to work with it, and I'm excited to start this webinar. So in the webinar, we'll start with, first of all, we'll talk about the logics of how the algorithm works, or how the slime mold, you know, how it acts, and then we will continue with exercises. We'll start from simple exercises to further understand the logics and the behaviors, and then we will continue with more complex exercises. And during the end, we will also see how we can extract various types of geometries and data from the organism. Okay, cool. So what I want to do is I just wanted to this is something whatever. Okay, so let's start with the, you know, the algorithm itself. So I prepared you know, like a few slides where we can talk about how the algorithm works, and then we'll go into Grasshopper and start building upon it. So the algorithm itself is composed of two main components. So first is the particles, and then is the grid or the voxels. We'll start with the particle. So each particle has some coordinates in space, and also a direction of movement, a direction which shows where it is heading towards, or well, in a way similar to us, right? Because we're always facing, you know, one direction. Okay, and these two components are quite connected with each other. So the voxels themselves, you can think of them as pixels, or I don't know if you've in the 3D version would be the cubes, Minecraft-like. So voxels are not just a grid, like an empty grid. It's more than that. It's like each voxel has a few main components that are quite important. So first of all, each voxel has an address. So for example, in this case, this is the address of voxel 00, and then it's 10, and so on. Why this is important? Because at each point in time, we can access the neighbor voxels by accessing the addresses of the other ones. So voxels store a lot of information. They can store infinite amounts of information. You know, as long as we have like infinite memory, we can store infinite memory. They store all kinds of data. So you know, they know what their neighbors are. They know what particles are in each of every voxel, and also you know, they store other types of values, like in this case it's something called chemoattractors. Chemoattractors are you can think of them as a number in our case for the algorithm, but in like how this will act in real life would be like it's like some trails that are left behind by the particles. So each time they interact with the voxels, they leave something behind, telling the voxels that they've been there. Okay. So let's go on to the algorithm steps. So there are 6 different steps. So we have to, you know, we have a particle that's inside a voxel space, and it senses, it turns towards the highest value. So it's always looking for the highest value. Once it found it, it turns towards the highest value, moves towards it, and deposits these chemo attractors, then diffuses and decays. And we'll go through all these steps just to make it clearer. So, okay, so we have this particle, and I was saying that, you know, we have like this vector, the white one, that shows the way it's headed towards. But also there are like these 3 other vectors. These 3 other vectors, the blue ones, are actually the representing what the particle sees. So it sees 3 things. It sees in front of it, to the left, and to the right. And the angle between these 2 vectors, it's called the sensor angle. So this angle can, you know, can vary. So it can have like a really narrow angle of seeing, of sight, or like a really wide one. And you know, it has this way of like looking around the voxels, and one second. All right, so with these sensor angles, what it does, it's like it looks around the grid values, but only in the grids that these vectors point to, and then it samples the you know, the number inside the grid. And in our case, the number, you know, the brighter it is, the higher the value. So in our case, it will sense this value because it's the lightest out of the 3, right? And once it senses this value, it you know, it sees it, and then it turns towards it, like here, and then it moves towards that value. Now, there's a difference between the you know, the how far it sees and how far it moves. So even though it can see this far, or it can see a lot further. It can only move, by a certain increment, the same as we do. Like we can see 20 meters, but it doesn't mean that in the next second we'll just, instantly teleport ourselves there. And the movement itself is like the increment of movement is the so-called speed parameter. So in each iteration of the algorithm, like you can think about it like as a time-based algorithm. So in each iteration, it does all these steps, and then because the computer runs very fast, we don't actually perceive them as being different steps, but this is what happens. And the increment that it moves is the speed, okay? So it moves, and while it moves, or after it moves, it will deposit some chemoattractors. And in this case, because the particle didn't move outside its voxel value, it will deposit in the same voxel, the chemoattractor. So this voxel will increase its value because there was a particle there. And the next step is diffusing this value. So by diffusing these values, you can think of this as basically the same as when you're blurring a photo and you're like the pixels around the main pixel are taking a little bit of that value and like they're mixing the values together. And after diffusing the chemoattractors, there's also a decay function. So that, in time, if the organism maps the whole space and we don't decay the chemoattractors, they will all at some point be, have the maximum value, and then the slime mold will be confused. So that's why the decay function. And this thing goes again and again and again and again. So I would say that these are the main steps. And we will take this and we will reference these slides. We'll go back and forth when explaining the algorithm. Okay, another thing. So in the plugin, in the Dropbox, you have you have the plugin itself, and you have a basic example. Also, I've recently added this value list, which is just a value list, but we'll need it in the future because it's not included in the plugin yet, and you can just copy it from there, and you'll just see in a moment where we need it. Okay, but for now, let's just start in Grasshopper. Let's see if there are any questions? Where's the chat? Well, I'm really bad at
there's a Q&A button at the bottom.
Oh.
That will be where questions are. But there was two, but I answered them already.
Oh, I see. Okay, good. Yeah, it's the same algorithm, yeah, as Fusarium. Of course, there are differences because it's not like exactly the same one. And I think my contribution to the algorithm is actually having an approach that lets you kind of control it from top down in some parts, as well as bottom up, but it just makes the interface like taking into account that we're using Grasshopper, which is a lot more user friendly than writing your own script. And also there are so many things that you can do in Grasshopper to affect the in easy ways to by placing attractors and so on, that I really wanted to take advantage of the Grasshopper interface and integrate this algorithm as much as possible. And you'll see in the exercises how we can go about it. Okay, so if we look at the Nuclei plugin, first of all, let me just I will drop the bifocals component. The bifocals component doesn't do much. It just helps us, preview something with the icon and the name, because different people prefer different kinds of ways of working in Grasshopper. Okay, so if we look at the algorithm, like the panels, we have an environment panel, a particle panel, and a solver panel. The environment deals with the voxels. The particle, well, you guessed it, deals with the particle, and then the solver is where the magic happens, and we also have some settings for how the data is interpreted through the solver. Okay, cool. So like if we take this one, the environment constructor, which is the first component, we can see that we have like already something constructed in our view. So I will just leave this the way it is, because it's basically similar to constructing a grid. You tell it how many divisions on X and how many divisions on Y, and also the the grid size. So we need this. This is one, and then the other one, the other component that I was talking about in the previous presentation, is the particle. So we have the environment, like the voxels, and the particles. And we also need the solver. Wait, sorry. I've actually, by mistake, selected the settings. So this is the solver. So these are the basic main components for, the algorithm. So let's start with this one. Like this one already has values, it's okay. This one, tells us that the particle position failed to collect data. So we need to tell it where the particles are. I'll just hide this, because I don't want to see many points. It's useless at this point. Okay, so we can create particles by, we can just reference some points. So by double clicking and writing point, I can access the point command. I'm actually going to access all the commands by double clicking and writing the name of the command. If you don't know what I've written, you have the name of the component here, and you can always find it by double clicking and writing the name of the component. So let's say I right click and set multiple points. This is how we reference the points. And then I mean, I shouldn't be telling you this because you're already intermediate users, but just saying. So we can, we can create particles like this. And so we have the environment, we have the particles. Of course, the particles have a lot of settings which are predefined for the moment. So let's just go with the predefined ones, and then we'll start talking about each one of them. And what we need to know next is that in the solver has to know how we define the particles, right? And also needs to know how we define the voxels. It's all fine. Another thing with the solver, because it's it's something that runs again and again and again, we will need a timer. So this timer is telling it how if it's 1 second, every 1 second it will try to solve another instance of the algorithm, but by right-clicking on it, we can set the interval to 20 milliseconds. This doesn't mean that if we have like a really heavy computation that it will be solved in 20 seconds, but it will just reset the timer. So, once the solution is finished, in 20 milliseconds, it will reset the timer. So it will try to make, to run as fast as it can. This timer, we have to connect it with the solver. So by left clicking on this arrow and connecting it to the solver, that's how we connect it. We should, by double clicking on it, it becomes gray, which means it's disabled. We should take a lot of care with the timer here, because if we have something that's not set up right, then it will, it will probably cause problems with your computer, and you'll have to restart Grasshopper. Okay, let's see. We have some Q&A. Okay. You can just you can just double click timer or double click and write timer. The timer itself, I have no idea what it is, but it's a Grasshopper component. And you can just access it by like this, right? Okay. Okay, let's see the questions. I'm getting an error message when construct particles. This is not like cellular automata at all. It's very different.
For the error, I'm thinking maybe they have an older Rhino. Usually this kind of.
I mean, if the installing of the plugin is simple, you just you just have to drag and drop it, right? Like you download it and you just drag it and drop it on the canvas. So there's not much you can do wrong there. What I recommend is that you restart your Rhino, and when Grasshopper reloads again, the plugin should be fine. I've tested it on both Windows and Mac, and it was working. I am using Rhino 6, so you should be using at least Rhino 6. Okay, where was the timer? Can it be here?
It's in param utility.
Oh, okay, utility. Yeah. So here is the timer for the ones that can't find the timer. Yeah, so it's in the first tab, params and utility. I can, yeah, param, utility, and timer. Okay, so let's move forward. So we also need this Boolean here. This Boolean, when it resets, when reset is true, it loads all the data of voxels and particles inside the solver. And then when it's false, it basically starts iterating. Of course, in our case, I will just hide this. In our case, it's only gonna show one step because the timer is not enabled. But when we enable the timer, you can see the particles start moving. We should also
Mădălin, just a quick note. I realized why some people are confused. They renamed the timer for those using Rhino 7. It's called Trigger now.
Oh, okay. So use the trigger then. Cool. Good. So another thing we want to know regarding this solver is like what is the iteration count. So I'm just going to drop a panel. You can drop a panel simply by double clicking and then writing // or you can write panel, but // is faster. And this will, it will be visible what iteration we are at. So if I reset it, this is going to be null. And then once I turn this to reset to false and enable the timer, the iteration will start going up. So you can think of iteration as the frame, right? Like what frame we are at. Okay. Good. And if we want to preview better what's happening inside this algorithm, there's a way to preview it, and we have to basically construct a mesh and then color it according to the voxel densities. You'll understand what I'm doing once I'll do it. It will be quite clear. So let's take mesh from points. Mesh from points should appear here in mesh tab and util, and it's coming from the I think it was from the MeshEdit plugin. So I hope you installed all the plugins because we will need them. Okay, so mesh from points needs a few things. It needs the points, the grid of points, the U and V direction is just another way of saying X and Y direction, and the colors. In our case, we didn't add any numbers here at X and Y. So let's just add some numbers so that it's easy to access them. 100 by 100. And these numbers will go in U and V. So X becomes U, Y becomes V. The points themselves are these ones, the ones that we had from the beginning. And you'll see that a mesh has been created. If it displays it like this in your computer, it's because you can find this display option, preview mesh edges, to preview or unpreview the mesh edges. I would say don't preview the mesh edges because they add extra information that we don't need. And then the color, for the color, so we want a gradient. And we will connect these voxel densities to this gradient, and then we can connect the colors furthermore. For the gradient itself, I would say let's make something that like the colors themselves should be quite visible. Okay. So you can either see the particles as this, or you can see basically this is the way of displaying the chemo attractors. So basically what they throw out in the grid values and how those grid values are and how they update, in the algorithm. Okay, cool. So I will do the following. I will group this and name it as preview. Okay. And another thing I want to do, just to make the definition more clean, I will hide these wires, because once we do this, and we will do it a lot of times during the this, we'll already know where these wires come from, and we don't need to see them every time. And then this way the definition is a lot cleaner. I will also unpreview the display for this. Good. Another way of like, if we want to get something a little bit more interesting than just 3 particles, spinning around like crazy, we'll need a lot more particles. So in order to do this, we can either create random points and populate the voxel field with random particles, or but the problem with that is that it's quite slow in Rhino, and the way I prefer to do it, I'm just going to rename this particle position so that we know what it is, and it's just more organized like this. I'll just add a cool pattern component, get the voxels position. So I have 10,000 voxel positions, because the way I defined the environment. And if I get in here and manage Boolean collection, you will see that it has true and false values. When it's true, it keeps the particle. When it's false, it removes the particle. So let's add a lot of false, and we'll have 1,000. Maybe too many false. So it's just right-click, manage Boolean collection. Okay, and here you can add or subtract or remove Booleans. Okay, so let's say that this should be good for now. And if we restart our solver, always don't forget to disable the timer when you're making changes, because all these changes here are static. So even if you make changes during the algorithm, it only reads the changes while the Boolean is true. So it will only cause confusion if you let the timer enable. And also now we are running at a really low resolution, but when we'll have like larger resolutions, or maybe you will want to render this at, I don't know, 1,000 by 1,000, then every error can crash your computer. So just be very careful with disabling the timer. Okay, and now if I enable the timer, you will see that something emerges. I think it's displaying like this because in my gradient here, the right side is not white as well. Okay, so now like you can already see that it's creating some networks between those particles. Because of the way the initial values are set up, the network itself will tend to minimize. So the more it runs, the more iterations it runs, it will just minimize itself. So you can see like these circles are starting to close in, and everything becomes minimized. Okay, I think I want to see like, let's use 100 and, oh, sorry about that. Okay, so let's do the following. So for the next exercises, I will want to have a grid that is by the way, you can also like just see the particles themselves, how they move. So you're not just you know, using the grid values themselves can be quite chunky at this resolution, but like this you can see, you can zoom in and out and understand how the particles interact with each other. Okay. I think I'll just use another preset, maybe this, because it's more visible. And for the next exercises, I would like to have a grid that's not square, because we will start talking about values, and it's better to have a longer grid, and you'll see why in a moment. I'll just have a look at the Q&A. Okay, so try to go true and false again, and also, you know, it's like very important. Just make sure that you connect the particles to the particles and the voxels to the voxels. The algorithm itself, like the error messages, won't be telling you that you didn't connect the right things in the right place. So, like for example, if I connect this here, oh, okay, this, well, this was quite straightforward, but I don't know if I do this. I mean, some errors you will understand why, but like you should really connect the particles to the particles and the voxels to the voxels so that it works. Okay. Okay, your particles are not moving. Did you try to enable the timer? Okay, so these booleans are not all false. If they're all false, then it will just delete all the particles. Okay, so guys, like a lot of the questions, you can answer them yourselves by just, you know, downloading that, the one, like just try, all of you, try opening the basic example that I've added on the Dropbox, and let's see if you still have errors there. I mean, at the end of the day, it's not even about like understanding exactly where components go, where each one goes, because you have the example, and you know, this is like really simple, basic Grasshopper stuff. After you go past this, like the real interesting part is like, you know, how the logics of the algorithm work and how you can use it to your advantage and make it do different things. And And actually, the thing is, like, I've planned a lot of exercises for today, and like we should be, going a little bit faster. I mean, there's so many questions. Like the
I
Boolean
would just
collection, Mohammed, you can just put whatever you want. It doesn't have to be the same as mine, as long as you just delete some particles, or you can just open the example.
I would just. It seems a lot of people are having a problem installing, but a lot of people aren't. I'm not. I tried it on 5, 6, and 7. It works fine. I think if you're having trouble installing, firstly, if you downloaded it, make sure you unblocked it in case it got blocked by right-clicking it, going to Properties, and checking Unblock, just in case. Make sure you restart Rhino after installing it, and yeah, so you see where he's going now. So where he is now, usually underneath Advanced, there'll be another thing that says Unblock if it's blocked. Make sure that's checked and hit Apply if that's the case. If not, try restarting Rhino, and if further not, try restarting your computer, and if further not, then I'm not sure, because
If
it's
none of these things work, but then again, like when you test the plugin, please test it with the basic example that I've attached in Dropbox, just to make sure that you've connected everything the right way. And if everything else doesn't work, like none of these things work, please make some screenshots, and we'll make a special folder on Dropbox where you can drop your screenshots and describe your problem, and we'll go one by one and see, where the problem lies and how we can solve it. But from what I've tested, it works. So yeah. Yes, most of all of the example files experiments will be showed on Dropbox, of course. But we will be doing it like as we go. Like, okay, let me just so this is how your basic example looks like from Dropbox. So like maybe we should just open that one, and then we can continue from here and start with the other examples. Okay, so for the ones that's working, I really have to continue and go on with the webinar. And also it's something that can be useful for everyone, even if you're having problems now with the plugin. I will make everything that's possible to solve it for you after this finishes in the following days. So please pay attention to to the logics behind the algorithm, because at the end of the day you'll have all the examples that I'm talking about here, and all these examples will will be available. This webinar will be available for 30 days after it's finished, so you can still rewatch it. So don't worry, like don't panic. Let's continue with the webinar, and because we have so many so many nice things that that we will do right now. So let's get into it, and let's talk about the the logics behind it, this algorithm. Okay, so if you see the differences in this one is that I've done like a different voxel field with 130 by 150 by 300. then the particles, they're a little bit denser than in the other one, but okay. And then I've also attached some parameters to each one of this, like each one of them has different values. These values actually, I think they're the same as, well, or very similar to the ones that are by default. So the reason why the particle component works, even though it doesn't have all the values, is that it already has some predefined values. So let's start with this. Like this will be our basic example. Cool. So in order to see the different values and how they affect each other, I'll just do it like this. I'll take this and copy it, and then I'll modify it, and then I'll do this again and again and again with new values so that we can like compare them. But in order to do this, by the way, like when I'm doing the copy, I'm locking the solver so that it doesn't take too many resources of my computer. Okay, so what I want to do is I want to move this display with on the right. So I'll get a move component with a y, no, an x value, x vector, and I'll just multiply, because the voxel size is 1, it's easy to multiply this x with something, and it will just move it right beside. In this case, I'll just multiply by 1. So, sorry, this is the, so I basically want to move this here, right? So this was here and I moved it here. That's all I've done, like simple basic move. But the reason is that, you know, I want to compare the results, and I'm gonna unpreview this one, and I'm just gonna leave this one, the previewed one. Cool. Okay, so the second one will produce a really similar result, as long as I let it run for the same number of iterations. Okay, but I wanna work with the particle values, and instead of like modifying these particles here, what I want to do is like I want to modify the way these particles interact with the grid values. So if I go back to the plugin, one thing that's important to see is the environment values. So what the environment values do, they basically, you know, they alter the way each particle reacts based on the environment. And I will explain this in a moment. Just bear with me for the moment. So we have the voxel values. Another thing is, please go to the Dropbox if you haven't done this already. Download the value list. I mean, I should have done it in the plugin, but whatever. I'm just going to send it to you like this. So this is just a list and that's it. And we need this list instead of defining it, I will just copy and paste it. When I'm pasting it, it's gonna appear here at the top. Okay, so you can see like this list, we need it because we will connect it with the type of voxel values. Like here we say which type of values we want to modify. Okay, and in order to do this, like first let's preview a map of what we want to modify. So I will do the following thing. I want to have, I really want to have like my speed being smaller on this part and larger on this part. So the higher I go, the more I progress on the y-axis, the larger the speed. So in order to do this, like for the voxel values, we'll need to assign the amount of like, if we have, in our case, we have 45,000 voxels, we'll need to have 45,000 values. So like, just to make sure that we don't make any mistakes, I will use actually the voxel positions. Okay, so let's look at this for a little bit. And with this point, I will construct the same thing as here, right? So I want to visualize this. But I don't want to visualize the voxel densities. I just want to visualize my, like we can do it with an attractor curve, like this way of like defining the values, or we can just do it with numbers. So let's do it with numbers, because you probably know how to do it with an attractor curve already, and we'll use that in future exercises anyway. So what I'm doing is like I'm taking all these points, all these grid points, and I'm deconstructing them. So basically getting the X and Y and Z values of this. I'll just go in Grasshopper, no need for Rhino for now. And I'll just work with this. So I deconstruct it. And what I want to say is like, the more you increase on the Y axis, the larger the value. So what I want to do, I want to remap the numbers. So these are my values, the Y values, and I need the bounds. So from where to where my values are. And we can see that they're from 0.5 to 299.5. So this is my starting domain. And by default, my ending domain is 1. So the way remap works is like, imagine you have a lot of numbers from 0 to 10. And if you want to remap them from 0 to 10 to 0 to 1, 10 becomes 1, 5 becomes 0.5, and so on. And this is something that is, you know, it works with other domains of numbers as well. So if we take these bounds and look at the remapped values, like their bounds will be from 0 to 1, the same as the target domain. And the reason why I'm doing this from 0 to 1 is because I want to put in a graph mapper. And this graph mapper will further alter my values. So these values will just like usually they just progress on a linear scale, but I want to have an S-curve. So that's why I'm actually selecting the Bezier type and I will remap these values. I'm actually gonna double click and remap the values because it's like it's quite heavy to remap them in real time because there's so many of them. And if I connect my values to this preview here and go back to Rhino, I should be seeing like this is how the values in my grid are. So the lighter the color, the smaller the values, the higher the color, the larger the values, right? So like, for example, if I do it like this, it will only get very large here. But let's say, let's say we have like an S-curve. What this S-curve does, it keeps the, I mean, it's quite obvious. It just keeps the, almost like having two values and a small area that they transition in between each other. So this is just for preview, just to preview the way my values will get into the voxel values. So once I've seen this and I liked it, I'm just going to disable it. I don't need it for anything. It was just for preview. Okay, so the environment values need, I'll just move this a little bit down the line, or actually move everything a little bit more on the right, just to keep things organized. Another thing that I like, I'll just put my particles down because, well, for the whole exercise, we'll keep the particles the same, and we'll just alter their values through the voxel values. So my voxel values need a voxel address, which is coming from the environment constructor here, voxel address. And my voxel values are, for now it's from 0 to 1, but let's just remap this domain again to make some values that make more sense, because otherwise we'll have a speed of 0, so we'll have particles that don't move. Actually, let's try this because you will see what happens. And then the voxel values will be connected further to the solver. So again, what I did is like I took this voxel position, I deconstructed this point, and I worked with the y values. And the higher the y values, the higher the value. The smaller the y values, the smaller the value. And this gave me this map where like the map of values of the grid. And here in the environment values, I can select which type of value I want to alter. And it needs the address and the value. And then I just connect it to the voxel value here in the solver. Okay. So 1 second, I don't need to preview this. So this was my first iteration. And in the second one, you will see that because the speed is so small here, they don't even move. And when they don't move, they don't deposit. So it's barely here where it reaches the same kind of status as this one. So let's say we leave it run for 60 frames or so. So you can see that this is starting to like, it won't be the exact same pattern, but it's like, it kind of has the same porosity as the other one. So it kind of has like similar traits. But here the speed is very small. So what I want to do is like, I want to remap this domain to have like higher values. Yeah, so in order to do this, I'll just remap these values, these numbers again. My start domain is from 0 to 1, like before, and I need to construct a domain for my target domain. So let's say the start value will be 1 as the one before, and my end value will be 2.25. I'm just making this up right now. One thing that you should know is that the way the voxel values work, they are like multipliers. So if my particle is in this voxel, yeah, so if my particle, one of the particles, let's say we have a particle in this voxel, and we know that this voxel will have a higher value than this voxel, then what happens, it takes the particle value and it multiplies it with that value. So that's the reason why the domain start is 1 and the domain end is 2.25. So what I want to do is like keep the same speed as the other one. So I want to have like the same kind of pattern here where the y values are small, and then I'll have like a different kind of pattern here where the values are large. So let's see what this does. So I've reloaded my values inside the algorithm, and you can see that I don't have any more problems here. Okay, one thing is that, I mean, we can preview the particles in the background here as well, but just not to make the algorithm more complicated, we'll just keep it here. Remember that we're displaying the voxel values here, actually here, but we've moved it here to just to be able to compare the two things. Okay, so if I look in the background at the particles, and I don't display those ones. This we should be moving a lot faster than this, but I think because the values are not that different from each other, 1 and 2.25, then we won't see a lot of difference. So what I suggest is like let's turn this up to 4. Actually, I think you can still hear me, like if I mute the audio output, right, Michael? Michael, can you hear me if I mute this output, or should I? Oh, okay, let me just do this actually. Okay, it should be good now. Well, since I came here. No, there's no constraint to the amount of iterations, so I sometimes leave it overnight and see what it does. Okay, I will share this, yeah. Yeah, so these particles got stuck to the borders. Yeah, it's something that I should be improving in the future. I think at some point I've done it, but I don't know what happened after. but the good thing about these particles, I mean, even though they stick there, they are not taking into account into the voxel values. And from my experience, you'll rarely use the actual particles like the points themselves. But it's something that I will fix in the coming iterations of the plugin. Okay, so let's start again. Now this time, remember, we have like the speed a lot larger here than here. And one thing you notice is that the pattern here is very articulated, and here it becomes very fuzzy, in the sense that it looks very much like this. And the reason for that is that you know, 4 is a big number, and if you multiply 1.25 with 4, you'll get number 5. And my speed is larger than my sensor distance. So if we go back to this part where I was explaining the sensor, like in this case, I'm representing the like sensor distance is like the amplitude of this vector. So in this, so if my speed, which is the white vector, is larger than my sensor, it means that even though I sense something very close and then I move past it, I always overshoot it. So it cannot create articulated patterns if the speed is larger than the sensor distance. It can create interesting artistic effects, but not articulated patterns. So one way to fix this is to increase the sensor distance. But I don't want to increase the sensor distance here because it will increase it everywhere. I just want to increase it in the voxels, so like as a multiplier. So what I'm going to do is like, I'm going to copy and paste the environment values. And the next, I will affect both the speed and the sensor distance with these remapped numbers. And I can, by clicking Shift, left clicking the voxel values and dropping it into the voxel values here, I can put both of them in the list. And now it will take two environment values and it will take them into account. And you will see that it will create something very different from the one we had initially. Okay, so this is what, speed and sensor distance, this is how they affect the algorithm. I just wanted you to like have these two things to compare. So remember here, we're starting at the same value as this one, and then we are increasing the speed and the sensor distance, and it creates this kind of like patterns that it's almost like we were zooming in, but it's not like zooming in because in the end, it's, if we look at it, like we have like a lot more complex things happening here with a lot more particles going around. So I think this is not necessarily the best display. A better display would be, even though it's not very aesthetic, would be this one. So if we look at this one, while it's moving, you can see like the way the particles are moving inside the slime mold. So it's almost like transporting those nutrients all over the body. So this would be, I mean, even if it looks very engineering-like, it actually does provide a bit more information with this rainbow of colors. So what I'm trying to say is that there are more complex things happening inside a strut here than inside a strut that's thinner. But yeah, I'll just come back to the initial one because it's just easier for the eye. I mean, this one has more information, but I really don't like the way it looks. Okay, so I'm gonna restart this and leave it at around 60 frames like the previous one so that we can compare them in an objective way. '62, 60, around there. So these are my two patterns. But remember, like if a particle, like the particle gets its speed and sensor distance affected only when it is in this area. So even if a particle, you know, starts from this area and then moves up, its speed and sensor distance move up. But then, you know, while it goes back down, like depending on where it is placed in the environment, then it will have the speed and sensor distance scaled accordingly. So in a way, like a good analogy for this is like if you think about weather, right? So if we have you know, rainy weather here, the cars will run a little bit slower, and here where it's like sunny, they will go faster. But when they turn back to the weather, like the rainy weather, they will start slowing again. Don't know if like it's the best analogy, but it's the first thing I had in my mind. Okay, so I'm gonna save this and I don't know why I gave it this name, but I will actually, you know, I have a file that's prepared with the whole exercise that I will give you at the end. But for now, I just, I'll send you this one, which is intermediary. So let's create another folder. New folder. And in this folder, I will drop the example that we've just done. You don't need the Rhino, it's just Grasshopper. So did it go well? Okay, so if you go to the folder definitions here, you will find this example that I've just created right now, so you can keep up. Okay, let's see if we have other questions. The initial distribution of value. So yeah, I mean, it's clear that the initial distribution of the values is affecting the result. Like, but it's not just initial. It's like the voxel values remain persistent throughout the whole time. And what it happens is like each particle at each point knows where it is in the space. And if it's in voxel, in this voxel somewhere here, like its speed and the sensor distance in this case will be multiplied by a value. If that value is 5, it will become 5 times larger. And it will behave in a different way. So this is uniform, everything is the same, and this is different. Like, you know, like remember the, you know, this map right here. Like, just to give you an example, if I were to continue with this kind of approach, where I only have like the high values here, you will see that this result so yeah, the voxel values are just meant to affect the behavior. So we can affect the behavior in many different ways. This is one of them, and I've started talking about it so that you guys can can start learning about it. Okay. What other questions? Yeah, so 3D networks will be available in the future. For now, we are looking at 2D networks. Yeah, they are constrained to a 2D plane, but yeah, we can call them pixels. I am calling them voxels because plans are that in the future we will be running this algorithm in 3 dimensions. You cannot apply in different parameters rather than rectangles, but you can, like, if you have a little bit of patience, you'll see that inside these boundaries, we can create any types of boundaries that we want. This is how you use the value list. There's not there's not a Nuclei download link in Food for Rhino. You can find it in the Dropbox folder. Okay, let's move on. Good. So what I'm saying is, like, if you like, there are other this algorithm is very complex, and it's like you can create your own version of it by modifying the values. It's similar to agents. So this kind of algorithms that are generative and bottom-up algorithms, they kind of, they have their own logic, and you have to understand it and co-create with it. And you might be used with a lot of algorithms that, just modify geometry from Grasshopper. This is like the procedural parametric approach, where you see everything, what you want to achieve, and you just achieve it with this. With this webinar, my goal is to get you to dive into this generative way of thinking, bottom up and top down. And we have a lot of things to experiment in 2D for now. And you will see that by modifying some things, and I'm probably gonna, in 5 hours, I'm probably gonna talk about like less than 1% of the possibilities of values or combinations of values that exist. But by looking at this, you will see how you can interact with it in different ways. And then we'll do some exercises and see how we can apply them to different things. So yeah, I mean the algorithm, or like the Grasshopper plugin itself, you just connect some components. Once you've done it, then you know it. But that's not all. I mean, actually, the hard part comes when understanding the values and understanding how the algorithm works. Otherwise, you will just be stuck at this initial aesthetic, and you'll probably modify the speed a little bit. But if you don't pay attention to, to the logics of why modifying different things affect different things, then it will be, it will be hard for you to actually control it and get anything else than this basic example. Okay, so already 1 hour and a half passed, so we should move on with the next examples. So what I'm suggesting right now is, like, you have this example, you've understood, or you will understand by reviewing it in the future, or rewatching this webinar. So what I'm suggesting is, like, don't try to do the same thing as me in Grasshopper now, because the values that I will modify now, like, it's more important to understand the logics than to do the whole Grasshopper thing again, because there's no point in that. You'll have the definitions anyway. And what's important right now is to understand the logics and why different parameters affect different things. So I just want to move on. And I want to talk about rotation angle and sensor angle. I'll just leave this simple as possible. I'll move the next iteration. Okay. And instead of a speed and sensor distance, I will just modify the sensor angle. So you can see that in this case, the pattern is more articulated here, and then it becomes like islands. The reason behind it is that, we are talking about the sensor angle, which is this angle between these vectors. And what's happening is that we are multiplying that that angle, like we are making it larger 2 or 3 times, meaning that if it's initially 45 degrees, then 2 times it will be 90 degrees. And then 3 times it, like, if it's very large, it tends to create this kind of islands. Yeah, so that's why we are getting the islands. And another thing is, like, what I've done here, I've oversimplified things, but turn particle towards the highest value. I've oversimplified things by having a rotation angle and a sensor angle that are similar. The rotation angle is like the angle in which the particle, like the amount that the particle turns towards the value that we want. So if we were to have like a different angle, then the results would be different. So first of all, I'll just modify this to 2 because more than 90 degrees, it doesn't make sense. And let's see just the sense, just the rotation angle. So in this case, I will sense the same as the first one. But then rotate a lot more. Maybe just emphasize this. So what, like you can see now that we have like a different kind of aesthetic. So we don't have islands, but we have these blobby things. The reason is because, you know, we are sensing something, and then instead of turning towards that grid value that's the best one with the highest value, we overshoot it by having a rotation angle that's larger than the sensor angle. So instead of having our particle rotate towards you know, the highest grid value, it will probably rotate, if it's doubled, like we can imagine that our particle is rotated around here, which means it overshoots again, and it creates this kind of things. But if I have the sensor angle and rotation angle the same, I'll just leave it to 4. All right, so probably here we're in that part where we've reached probably around here 360 degrees. So they basically don't have any logic anymore. They're just rotating around themselves. And then we reach again a smaller angle. So actually this is 180, and when we reach 360 again, it becomes the same pattern as here. So I'll just put this to 2 so that it's not so confusing, and we'll only get islands here on the top. Yeah, so what you can notice is the fact that here is articulated, it becomes less articulated, and this is like a state in between articulated and insular. And then, of course, when the rotation and sensor angle are very large, the particles become disoriented and they just rotate around themselves. Okay, so I hope this kind of makes sense regarding the sensor angle and rotation angle. I'm just talking about the logics, but trust me, there's so many things that you can discover on your own by playing it with it. But for now, I just want to show you a few different patterns and see how they are created. And this will be kind of like your library of ingredients to know where to start from. Of course, you can combine sensor rotation with speed and distance, but this is only when we're only taking 1 or 2 at a time. And you can combine more of them when you'll become more advanced and you'll form an intuition of how this thing behaves. Okay, let's move on with the next pattern. Let me remember what I wanted to do in the next one. All right. Okay, so we were talking about yeah, whether we can yeah, we will I'll show you. So like what we'll do now is we'll play with the density. So like our grid values are, you know, most of the time they're empty, and usually people that code, they don't get through all the trouble of importing an image or like a field or whatever as an initial density field for the like the grid values. Because, you know, it's a bit more complicated, but in Grasshopper we have like it's so easy to add different values. So I mean this is gonna show you one example where you can see how different densities can like affect the algorithm. So what I want to play with now in this next one is I want to play with maximum density. So this meaning that wherever a particle is on the field, the grid will not get a value more than this one. So this is like a cap, like that grid, like that voxel can never get a value larger than that one. And we usually use this with when we want to have like some kind of obstacle to like so that we make sure that the particles, you know, don't go there. 1 second. Okay, so the values, okay, so the density, the grid values are always between 0 and 1. So if we put values, like in my case, from 1 to 2, they won't affect anything. So I'll just put them from 0 to 1. So you can see that from the beginning, these values won't be more than 0. So you know, this has some effects, some interesting effects. One of them being the fact that all the particles will migrate to the areas with more density. The idea is that, you know, the organism is searching for food, and in the places where it doesn't have food, it will try to stay away from there because it's just a waste of time and energy. So yeah, we can see how the values migrate to better areas with where they can create, you know, where the organism can evolve. Like in this area, if we look at it, like these values are very close to 0, and this one is very close to 1, so they will migrate there. So if this is close to 1, it won't affect the voxels at all, because it was the same condition as before, like they can reach values from 0 to 1. But what I'm saying here with the maximum value of 0 is saying like, look, whatever, how many, it doesn't matter how many particles are here and how much you want to deposit, it just cannot be done. So just go away from here. So this is what happens and why things become like this. But I wanted to show you another way of creating values. So one way is like through Perlin noise. And Perlin noise uses a similar approach to what we've done here. So it needs positions of points, and it will create some values. Let me just show you. Okay, it can create values like this. And if we make the scale smaller, we can create different types of values. And we can also play with the way those values are. Sorry about this. We can also play with, like the way they are distributed. But let's make the scale a bit larger so that it's quite clear where we have smaller or larger values. I believe that the bounds for this are from -1 to 1. Okay, so we will have to remap this. So I'm just gonna get rid of this. Actually, I'm gonna use this point. I'm gonna remap these values that are coming from this component. Perlin noise is a really nice spice for algorithms. You should definitely check it out. It's always good to test algorithms because you can create this environment that's more smooth or jagged, and you can see how easily see how your algorithm works on it. Okay, so we had this, and I wanted to remap them from 0 to 1, and you'll see that if I just, this is not the whole story. Actually, the whole values are from 0 to 1, like here. And I can also like increase the contrast. So for example, if I do an S curve again, you'll see that the contrast is way increased. I mean, this way of working, instead of working with attractors like points and lines, this approach is working with data. And I find it to be more relevant because, we can extract data from anything, and we have so much available data. And at the end of the day, what do? We just, place points by hand or lines for attractors. I don't know. I mean, for me, getting getting values from data is much more interesting than using attractors. But that doesn't mean that, in some situations, attractors are the best way or the best approach. But they are not the only one. That's for sure. Okay, so these are our values, and our values from 0 to 1. Okay, I mean, I don't need to remap them anymore because this is also splitting values from 0 to 1, but whatever. Okay, so let's see this one. Okay, so you can see that, you can control it in various ways, like the same thing that happened before on the y-axis, like having the maximum density very small here, so the particles ran away from that area. The same thing is happening here again. I'm gonna play it again. So these areas are areas where no matter how many particles, they will never have density larger than 0. And this will just scare away the particles, which will go away from that area. Okay. So this is how you can control the density. But there's another way where you can control the density in a way that you can have minimum values in the sense that you have some values that no matter if they have particles or not, they will still remain high. So I'll just copy this and turn this into minimum density instead of maximum density, and I'll leave the exact same map. And here I need to move this a little bit further. Yeah, so object not set to an instance of an object is, when you don't have this thing where you need to reset it so that it gets the values. Okay, so in this case, what happens is that these values will always remain high. And the other ones can have whatever values the slime mold gives it. We can also like remap it because 1 is a bit too high. So maybe let's just say 0.25. So in this case, I just want to have like a hint for the slime mold telling it like, okay, maybe you should go towards those areas. They're not exclusive, but there you'll have better conditions. I think the values are too small to make a big difference. Maybe 0.5. So yeah, you can see that the pattern here is quite different from, I mean, it's becoming different from the one there. Okay. Another example that would be interesting is like to actually use some geometry as obstacles. And I want to do this, and then we will, after I finish this, we'll combine the minimum density and the maximum density in this next exercise. And the next one will be based on having a vector field in the grid. And that vector field will tell the slime mold whether to move in one direction or another. Yeah, and then we're kind of finished with this first exercise. Yeah, so but let's just go ahead. I just want to see if there's some more questions. Yeah, I mean, you will, Matthew, you will see, like, I mean, it's quite clear that there are some ideas in some points, but at the end of the day, it's not like, I mean, you're not like this person that sees an algorithm and in 5 minutes understands what it does. We're not, I mean, I've been writing this algorithm and I'm still understanding. So at the end of the day, it's about working with it and forming an intuition of yourself. And the top-down approach is kind of like a negotiation between what you want it to do and what it can do, and it's somewhere in the middle. But for things like this, where you have obstacles or places where you don't want it to be, it's easy. But yeah, I mean, it's like playing with it, and you understand some behaviors, and then you can add them to various places. Yeah. Okay. Yeah, I mean, this is add attractors. Yeah, I'm not adding food as attractors in the algorithm, but you can consider putting the minimum density as you can consider it as food. In this case, it will affect the algorithm in different ways, because at the moment the slime mold has a fixed population, so it's not growing. But in the future exercises, we'll also see the importance of food as well. Okay, so let's move on. I would like to add something physical, like a place where we can like an obstacle, like a physical obstacle. And what I want to do to like get this physical obstacle, I'll just make some text. Let's write DM. I have. Okay, I'll just unpreview this. So I have this this brep, and I am going to okay, so I'm gonna reference that brep and use it as a way to create obstacles. So I've referenced it in my Grasshopper, so I can just hide it now. And one way to create obstacles is so it's still with this strategy, maximum density. So let's just do it like this. Points in brep. Point in brep. So I want to check if my voxels are inside the brep, and with a call pattern, I can actually get them. The problem here is that I have two breps. Okay. So I need to graft this list. And I mean, it's the same as working with multiple attractors. So I'll just go ahead fast with this stage, not explain it. Okay, so for each brep, we'll get the values for the points, true or false. I have to flip the matrix and one way is to compare. So I will get two values in each list when I flip the matrix because I have two B-reps. And I can compare them, but instead of doing that, I'm just gonna do mass addition. So if there is a true, meaning there is a point inside the B-rep, when it is true, it is considered as 1, and it is when it is false, is considered as 0. So what I'm interested for each point is to see if it's at least in one of the B-reps. And if it's in one of the B-reps, I'll keep it. If not, I won't. Okay. Let's see the list. We have zeros and 1. Okay, and I need to, I can just flatten it. Flatten my tree. And I'll have these values. And now when I enable this, okay, so this is a little bit larger than my grid. All right, so we have these points. Good. And these points. Okay, so the one thing that I want for sure is like when I create my particles, I don't want any particle inside this point. So my particles will be everything besides those points. So these points here, I was taking the whole grid, but now I only want to take these parts. So I could have created like a part of the plugin that dealt with this, but I'd rather have you do your Grasshopper work, because instead of like using some fixed ideas that I had for the plugin, like this you can customize and add your own. Maybe you want those letters to be fuzzy instead of like strictly included or excluded inside the B-reps. So it's up to you to be creative with those things. I'm just showing you the logics. So in the end, these are my initial particles, where they are placed. Another thing that I want to do is, if you remember, I had these values 0 and 1. So if it's 0, it means it's outside of the B-rep, and if it's 1, it's inside of the B-rep. I want to write an expression. And in this expression, what I do, I'll use an if statement. And the if statement goes like this. If something is true, then do something, else don't. Or else do something else, actually. But it's not displaying it here. Okay, I'll just. So I am going to do exactly this. So again, I know that the ones that are, wait, what was it? Which one is inside and outside? True if the point is inside of the B-rep. So true becomes 1. Okay. So if x is 1, meaning it's true, it's inside of the B-rep, then make it 0, else make it -1. And I'll tell you why in a second. You can see that, let me find, I know it sounds a little bit complicated, but I'm just turning zeros into minus ones and ones into zeros. That's all I'm doing. And the reason behind it is that in the places 1 is true means that it's inside that letter. And I want that letter to be empty. So that's why I'm turning the ones into zeros. And the zeros, the ones that are outside, if I turn them into minus 1 means that the voxel will remain the way it was before, so it will not be affected. So it usually takes values between 0 and 1, but if it is exactly minus 1, then it won't be affected. So maximum density voxel value. So you can see that now this is cropped out. Let's see the others as well. Maybe I'll just move this to the center or something, and then just restart the thing. Okay. So this way you can create obstacles, like meaning that your particles will not go inside there. Right. And also it's the same way, like if you can have like, you can think of the voxel field as a bounding box. And if you want, for example, an actual Petri dish, so like the boundaries of your, I don't know, of your grid to be like a circle, then you can just crop out the circle. So like, for example, let's say, we have like, we just want to run everything inside this circle, right? So I need to make a brep here. And okay, I don't need this anymore. And with this brep, what I'm going to do is I'm going to do the same thing, but just because I have one and not more, I'm going to use it like oh wait, I forgot that we are working here actually. That's just a preview. So okay, I need to reference my brep. Come on, come on. Okay, I need this becomes the place where my particles are born. And in this case, I want it inside the circle, not outside of the circle. So if x is 1, then -1, else 0. So I just revert this. And by reverting this, one second, I think I might have done something. So my particles. voxel values. Okay. Can be that I was good. -1. Yeah. Okay, so like for example, this is the way to, you know, only run everything inside that circle. So even though, you know, it's always a rectangle, it's up to you what, you know, what the, this is like just like a bounding box. Otherwise you can make whatever shape you want and then they can just run inside that shape and that's it. Okay, but I was like, yeah, I was meaning to combine the minimum and maximum density. And I just, let me just remember. Well, I think like the next, like, let's not do the combination now. We'll do it in the next example, and you'll understand there better where we need to do it and how we need to do it. All right, so let's just keep this like this. And I just want to show you the next part, which is the one with the vector field. And in this one, I'll take, so again, all my particles are good. Then my voxel values. Okay, so for the voxel values, I will create some values now. What's important here is the fact that in order to give it like an angle, we need to find this local angle setting from the value list. And this will give us an angle. I mean, one easy way is just to add an angle like this, and they will all go towards that angle. So it's almost like having like a vector field behind it. And you will see that everything pushes towards the edge. Now, when working with vector fields, one nice thing is like here in the solver settings, we have a setting called wrap. And what wrap does, and this is, by the way, this is a dynamic setting. So if I move it to true, you will see in a moment what happens. Well, I mean, it's too late because it already made its mind up. What happens here is the fact that this particle will is able to move past its boundary, so we won't have any particles that are stuck to the boundary. And what happens is that it moves in the other side. And one way to show you more exactly than just saying on the other side is like this becomes like continuous. So you can see that this moves there and so on. The same thing happens. One second. So, you know, with a small patch, you can actually make an infinite kind of a pattern. All right. So that's one way of controlling the vectors. So basically, this value just takes the angle, and that angle is in degrees. In our case, is 45 degrees, the angle. But if we want to have like a vector field behind, I'll just use this purlin before, like we used before. And I'll create a vector field with it. So I'm gonna remap these numbers. Let's say 360. And what happens now is the fact that, okay, okay, to preview this, I'll just, I'll create some lines, like not vectors, lines. I just find them easier to preview. And with unit X, so sorry. So I need to move these points 1 unit on the x-axis to make the second point of the line, right? So I move this point, and my vectors are these ones. You see many vectors for each grid value, and I will take these vectors and rotate them . And you can see that those values from the purlin translated into vectors, but they are very chaotic right now. Like just imagine that going from one grid value to the other, it turns so much. So I will just make like by decreasing the value of this number. Also, by the way, I've done a mistake here. I forgot to tell it to have degrees instead of radians. Okay, so that was the problem. Okay, so let's say that I have this grid like this vector field. And in order to insert this vector field inside my component, I need to do a few things. First of all, I'll just turn this line into a vector just by doing this. I can turn it into a vector. And then I have to get the vector angle. First vector, second vector. But the problem is that you will get like if you have any experience with Grasshopper, you will know that this vector calculation is not very good. So we need to do the cross product as well, and the cross product don't worry, you have this everything like in the example files. So you will see that the Z value of the cross product is also with -1. And what happens is that it tells us which plane it took into consideration, because it usually takes XY plane, but the Z of the plane, it's either up or down. So we will have to pick by selecting the one, if we need to pick if it's the angle or the reflex angle, the one that's right. To be honest, I don't know why like this is not something done in like a good way in Rhino, but whatever. So another thing is like we are working with degrees instead of radians, because these angles are in radians. So let's turn them into degrees. And the only thing we have to do is like multiply this. I'll just set this Boolean to true so that we don't multiply with things that will affect the angle. So it's only -1 or 1, the only values that Z takes. Anyway, like this is the proper way to get the right angle. And we'll get this angle inside our voxel values. And you'll see in a moment what happens. So instead of having this, which is more or less boring, although it can be interesting because, you know, like it's very directional. One second. All right, so you can see that they are moving according to the vector field. I mean, you have to believe me, otherwise, no, I'm joking. It's easy to check. We can just, like, let's just hide the initial one and do the following. We have this, and we have these lines. Oh, not this one, sorry. The rotated ones. So you see, like, it kind of makes sense, and it's like this is like a top-down approach, which is it's quite strict with the algorithm because it's the same as minimum and maximum density. It constrains it so much that you know, it's the best way to make sure that it will listen to you. But this takes away the surprise, and at the end, the behavior is not going to be so unpredictable, unexpected, unseen. It will be something that you will probably see already if you already have like you know where the vector field is and you know how it will act and go. Just wanted to mention here that the larger that number for the wow, oh, is this the number? Wow, this is a very large number. Just want like a lot smaller number. If I have like a smaller number, like it will, this means that like the directions won't be so much concentrated in some points. So in this way, it can like move smoothly. So for example, maybe this is like too small, like this number, but let's try 60. I'll just hide the vectors for now. Well, yeah, this way it gives it place to, move around and not necessarily concentrate on certain areas. I mean, yeah, it still concentrates in certain areas, but taking into consideration that we have the wrap turned on, then it means that we can take advantage about the fact that these particles that go here will appear here again, and then they will continuously move. Otherwise, if everything is circular, like the vector field, and everything, like that number is large, like everything becomes concentrated in some pockets in the middle, and when the minimization happens, they will all wind up like this. Of course, you can use any vector field you like. I mean, you can either use like the field components in Grasshopper. You can create your own vector field, and the algorithm will follow, as long as once you get your vector, your vectors, the X and this, just make sure that you use this way of feeding the angles further, because otherwise Grasshopper messes them up a little bit. Or maybe it doesn't mess them up. Maybe geometrically this is the right way. It's just that for me, doesn't make much sense, but whatever. Like, yeah, just make sure you use this. Okay, good. So let's take like a 5-minute break. I will upload all the definitions until now, and actually like the clean version, not the one that I've done now, like very fast. And you can have a look at it. And also when I get back in 5 minutes, I can answer some more questions or suggestions. So yeah, let's have a quick break, because it's been quite intense. And yes, algorithm explanation, I'll add this to the Dropbox.
So just two things from images people are sending me. If any of you are getting a Grasshopper breakpoint when you open it, and it says something like Nuclei component library was built against a newer, minor version of Grasshopper SDK, that means that your Rhino needs to be updated. So if you get that message, please update your Rhino. That's why it's not working. To the newest service release of 6, or just get 7, either as a trial license or whatever. The other thing is that some of you seem to not be able to see the simulation, and from what I realize is that some of you are not hiding the display of your point grids. So you obviously will just see the points instead of the because the points will be covering the simulation happening underneath. So make sure you turn off the display of your point grids, and make sure that you switch the toggle on the reset solver, and make sure that your timers or triggers are being played. So those are the kind of common issues that I'm seeing with people having trouble making this work.
For urban design, I have an exercise exactly for that. Actually, I think I have two exercises that might work for urban design. So you'll see this in a moment, how we'll get like real maps on which we will work with this algorithm. Yes, so my plan is like for updates of the plugin. So my plan is to release this plugin on Food for Rhino, but this will happen later on. I first have to develop the the 3D version and also like example files for that. And this one took like around 2 months to develop. I mean, I wasn't working all the time only on this, but yeah, when I'll have both of them, you'll have everything on Food for Rhino with example files, and then you can play with them. Also, we are planning. I think we're 90% sure that there will be like a sequel to this, where when I'll have the the 3D version ready, we'll also do another webinar on the 3D version. But yeah, I mean, you will get the updates, and I like my personal take on this is like I wanted to see your opinions first and see how you guys interact with it, and like what you think is like where are the points where you would like it to do one thing or another, and then I can develop the further develop the 2D version and also the 3D version. So like you're basically my community at the beginning, and based on on your requests and what you think is important, that's how I will further develop the algorithm. So yeah, I mean it's uh, it's yeah, I mean, okay, so question, Matthew. Related to performance, have you experimented with ways to score with other simulation packages, combining the plugin with Ladybug, Honeybee? Well, I mean, I'm not an I mean, this is up to you how you want to use it, and you can definitely get data from like solar radiation, for example, and then as long as you understand like the logics of the plugin, then you can interpret that data and feed it into the algorithm, and it will produce things depending on that data. One thing I need to mention is like even though they are algorithms and they have mathematics behind, at the end of the day, it's up to us humans to interpret that data. And whatever algorithm you're using, still at the end of the day, it's like there's no solution, objective 100% solution for something. So even with solar radiation, you can make some mistakes in the algorithm, and at the end you won't get like an objective result. So that's why we are here, because otherwise the algorithms will just run by themselves. We make them produce results, and then we look at these results and see if they make sense or not. I mean, this can definitely create like very efficient transport network, or depending on the parameters, you can create a very inefficient transport network. So it's, I mean, the logics behind is that it creates a transport network that is good, but it depends on the parameters that you feed in and how you interpret that data. So it's really up to you. Yeah, so like, would it be possible to simulate photosynthesis and influence the growth through variable parameters such as light intensity? Yeah, definitely. So you can, like, it's all in the density at the beginning. The same thing with the food. Like, density can become food, and or density can become light or whatever. These are abstract parameters that you can turn into something that makes sense. And you will see in the next examples that, you know, I mean, so far we've only discussed about the parameters and how they influence the behavior, but more complex behaviors emerge when the population is dynamic. So when it actually grows, because now basically we're creating particles everywhere, and then we're minimizing those transport networks. But when it grows, and it grows in an environment, and that environment is defined in a way or another, then, you know, it makes more sense, or it's like you can see some behaviors that relate to that environment more when it grows. I don't have an example of single points acting like the food for the growth, comparable to the city connection routes. But yeah, I can definitely have a look at that. I think I don't know. I mean, for me, at the end of the day, even though those examples are, you know, what happens with the slime mold in reality, it's, I don't know. I think we can go beyond that. Yeah, I can explain how to record videos. This will be at the end, of course. Yeah, that's the fun part. Also, be prepared to leave it run overnight if you want to record high resolution videos. You cannot have multiple bounding boxes, Walter, but you can, inside your bounding box, you can, like the way I've done it with the two letters DM, you can have like a very large box which has two smaller boxes inside, so you can have like a workaround for that. The reason why you don't have multiple bounding boxes is because of the voxel logics. They don't work. They simply don't work like that. But like I said, you can have like workarounds. Okay. Okay, can I please explain the role of the sensor angle again? Sure. So our particle is placed in a grid or in a voxel field, okay? And it faces some direction. And the sensor angle is this angle here. So if this angle was smaller, then the particles will move more in straight lines than in circles. If the angle is very large, they will, like, those circles will become smaller and smaller. This is what the sensor angle does. But it also has to be paired with the rotation angle, because if you have like if you have the sensor angle and the rotation angle, Then you have like a simplified version where it senses something like in this grid value, for example, and it rotates towards it. Like this is the highest value, and it rotates towards it. Then it moves towards it, and then again it will have the, it will get to the same point here where, like, but just imagine that it's turned, and then it will sense again the world around it. So that's what the sensor angle does. It shows it like it's like the field of view, like we humans have. Like I cannot see something behind my head. It's the same thing with the sensor. It just tells you how much or how little you can see around you. That's what the sensor angle does. And then the rotation angle means once you've sensed, like if I can sense this much, but I can only rotate just a little bit, then you can imagine that the behavior will be different than when I can sense this much and then I can rotate this much. So that would be the sensor angle and the rotation angle. I hope it's clear. So you want to extract the boundaries of the slime as curves. Yeah, you can do that. We will get to that point. Sure. Yes, we can shape it, like we can have an environment, like an existing environment, like an environment map, either be like a city or but when I say city, I'm basically saying like, okay, these are the streets, and imagine your car. You can only run with the car on the streets. If you go outside of the streets, you run into buildings. Or you can like use the streets as guides and then have places where those things are like just guides that get neglected, and then the algorithm creates its own streets. Like one example of this would be like in the promo videos. Like you can see that there are places where it strictly respects the grid of the city. This is actually a map from Brooklyn, I think. And then there are places where you don't, when you let it do its thing, and then it, let's imagine that here you have like an area that's not built, and you want to build like the next neighborhood with a different street map. But also you have to take into account the existing neighborhoods. So here it goes strictly on the streets, and here it has a lot of freedom to go around in different ways. Okay. Another example, like with the terrain, for example. Like if we look at, this example, like in these dark areas, like let's say we have a river, and the effort to build a bridge is quite high, so it only builds bridges where absolutely necessary to connect itself, but otherwise it will go around these areas. And here I've just like you can see behind the map, and the lighter areas are like You can also consider them as height. So, or you can consider them as food. Food meaning that in this case that these areas are okay for it to grow, but in these areas, for example, the conditions for growth or expansion are less suitable. So you will see that it kind of stops in the places that it doesn't have proper conditions, and it creates networks in the other places. Also, in this example, you can see that it always tries to go in the places with the best chance of developing itself. So the areas that are lighter are the places where it tends to grow, and the areas that are darker are the places that it kind of goes away from. And the same way that I've shown this, I mean this kind of thing can be maybe like you can translate some kind of map that takes into account light. I don't know. But again, I mean, it's data. We're working with data, and it's abstract data, and that data can turn into different things. I mean, I will never make a component that says light, and then you put light on the on the slide mode. That's not. I mean, that's not my interest. My interest is to, it's up to you how you manage that data and how you think about it. And it's your role as a designer to make use of large amounts of data and rationalize them and turn them into something that makes sense, I think. Let's see if we have other questions. I don't know what DEM is. Yes, you can just enable the timer or the trigger. You should, in case. So, okay, let's go to behavior. And if, because, it's like, let's see if I'm right. So make sure that this is not disabled. Another thing is like your timer has this tick value here. And if you undo it, you can enable this, but it won't run. So make sure that these signs are always ticked so that your timer works. Yeah, but geometry is data. I mean, it's like if you have other plugins that you input geometry, that geometry will be translated into data in the end. And like attractor points, like you can easily do attractor points by, like it's the same way. Like I've done the DM letters, for example. Those can be your attractor points, or you can definitely create, you can create attractors. Like attractors, what they are at the end of the day is like it's data as well. Like even if you have like, if you just think about it as a geometry, that's the attractor point, in the end that's data. And it's like I can show like an example, just because attractor points are like something that you guys want. Okay. This is my attractor point. And what an attractor point is as data, it's the following. It's from this point, you get a distance to the voxel position, and then you have to remap these numbers. This is an attractor point. This is how an attractor point is represented in terms of data. So, you know, it's just a different way of looking at things, but it's as simple as that. Like, and it's up to you to, you know, to create this. And if you put this further, it's like it's the same thing. And you can, yeah, like for example, let's say we only create our particles in this area. Yeah, this is my particle position. And then I have my voxel values. And let me just get like a value list. And I'll just put like the maximum density. And actually I need to like have higher values here and lower values there. So the other way around, because otherwise it's not going to attract, it's going to repulse. I don't know, maybe like just something like this. Okay, so I can, okay, voxel address. After, no. And you'll see that with time, it will tend to go there. Like considering the way that the values are now, it's like minimizing the transport network. But like if I were to go into settings, and this is an important value, like the diffuse, how much it diffuses into the environment. If let's say if it were to diffuse more, on a bigger range, and this will just go faster there. But you will see like, because I think that like points and attractors are just like a very basic ways of looking at the world around us. But it's more like in the next exercises where we'll actually have growth, you will see how it develops according to values of attraction. But even in this case, like it will like, if we leave it long enough, it will settle around here. I mean, there's no other way, because this is where the food is, or like where the best conditions are, however you want to see it. But it's not something that, you know, if you put like an attractor point, it will just go straight there. Another way you can look at it is like, I don't know if like the local, I don't know what this will do. No, I have to visualize it to understand, but like you can also put like, if you want an attractor and if you want everything to go straight to that point, you can make a vector field with like a point, an attractor point, and then put all the vectors to, you know, go towards that point, and then it will just develop in that way. But the way the slime world works, it's not like that. It doesn't see the environment in a way like it doesn't see far away. The way it works is like it basically first, like when a slime mold, I mean, you can look at the videos that I've uploaded, and the way the slime mold works is let's see if I can find
the
some
universe
images.
is
Talking about the universe. So you see, like this, like what it does here is basically it maps out the terrain. So it doesn't know for sure that it has to reach here. It just has enough food so that it develops itself a lot around these areas. And when it finds, like I think in the maze, it's just more visible. So it doesn't know how to solve the maze from the beginning. But what it does is like it maps the whole territory, and then let's see this maze. Oh, it's not very clear here. But for example, like let's say it started from here and it ends here. Like it will, if it has enough food, it will grow around the whole. Oh, it has food here and here. Okay, so it will grow everywhere. And then what it does is like in the areas where it doesn't have enough food to sustain itself, it just retracts from that point. And then it just keeps a connection between the first point where it has food and the last point it has food. So basically, you know, it doesn't know from the beginning where it has to go. It maps the whole territory, and then it creates the minimized networks of transport from one food to the other. Same thing as here. It maps the whole terrain. It doesn't know from the beginning that it has to find this point. But, you know, after a while, those struts are connecting the food. And where there's not food, there's no connection. Also, of course, they still have some connections between some parts, because the way it works, it's like it tries to connect all the food sources, but also connect with itself so that it can reach different parts of itself, even parts that don't connect food, but they are important for the organism itself, in the sense that sometimes it just needs to build some networks to expand itself, or it needs to feed some parts because reason A or B. But in the end, if you leave it long enough, it will just live and connect the food. Yeah. Okay.
I'm thinking maybe we should leave some more questions for later.
Yeah. Okay. So another thing that so what I'm thinking right now is like I will like the next exercise is about growth. So the Grasshopper file itself is fairly simple. So I will share it with you on the definitions folder. This one is called dynamic population, and we don't need to do anything in Grasshopper. You just like we'll look together at the way it works, and after that we will discuss the logics behind why it works like this. Okay. All right, so this is like very exciting because the behavior is going to be a lot different than, I mean, not a lot, but quite different. Okay, so I'll let it run. One thing that you'll notice is that the population is increasing. So this is the particle position, and we like the number of particles is increasing. It's also decreasing, so depending on some factors. One thing that you should take into account is the fact that in this definition, we have the solver settings as well. And I've mostly kept everything similar to what we had initially. I just increased the diffuse range. This means that it will diffuse more in the environment. And also, I think in the particles, I've also increased, no, I didn't increase too much the amount of deposit. Yeah, the more it needs to deposit enough so that it can diffuse in the environment, because if I were to increase this a lot, and I will do it at the end after it grows, because this one needs 1,000 and so iterations, it can just disappear, you know, it can just diffuse itself out. So, but more diffusion means that it's in exploration mode. So the more it diffuses, the more it spreads around. The less diffusion we have, the more minimized the networks are. So you can already see like the way it's developing, and this actually, aesthetically speaking, it also resembles the way the slime mold looks in reality. Okay, now other things that we have in the solver settings, which are quite important for the population growth. We need to have dynamic population here. This Boolean has to be true. If I turn it into false, the population will stay stagnant. But when you increase the population, and then it develops further, you know, so it grows. Another thing is, like, here in the particle we have two settings for particle, and those two are related to dynamic population. So first we need to tell the particle that we wanted to divide and we wanted to die at some point. And then we have some parameters for each one of these. And these settings go inside the particle settings. All right. So the way the particle division works. So it's like this. The division range. Division range meaning, I'll just go back a little bit to the grid. So if we have a range of 1, it means that if this particle is in this grid, 2, 2, it means that it will look one box around it. So 1, 3, 2, 3, 3, 3, and so on. Like the ones around it will be the ones that it checks in the grid. So the way the division works is basically it checks the neighboring grid and it counts the number of particles that are in the neighborhood. And so, for example, in a division range of 6, it means like that we'll have 6 values, 6 boxes on the left, and like we'll have a lot of boxes, right? We'll have 13 multiplied by 13, which is 169, I think, whatever. And in those number of boxes, we'll have some number of particles. And the division works like this. If we have between 100 and 500 particles, then divide. If we have less than 100, don't divide. If we have more than 100 particles, don't divide. On the other side, the depth settings, the particle depth, goes on the other way. If we have in the neighborhoods of 1, right, like this range, if we have less than 0 particles, then die. Well, in this case, that doesn't make sense because we will. No, actually, it makes sense because it will count all the particles except the particle that's looking around it. So yeah, if we have like particles that are like isolated, like the ones that, for example, we were talking about that were at the edges of the grid, and or particles that are isolated, you know, like just wandering particles that are not connected to the main organism, then they will die because they don't have any neighbors. They will look around them and they won't see any neighbors and they will die. Also, there's another thing called overpopulation. If you just imagine that if you have in this 9 boxes, if you have more than 100 particles, those particles, like it's the same as in nature, it's overpopulation. Some of them have to die. They can't all live together with the same resources. And it's up to us to decide these factors. It's a good thing that we are not working with real things. It's just an algorithm. So, you know, if some particles die, it's just life. Okay. The other settings, I kind of kept them like consistent throughout all the definitions because I wanted you to see, because if I change everything every time, there's so many parameters that at the end you won't know which parameter had more influence on what. So I just kept them the same, but of course if you modify these numbers, you will get a different behavior, right? So I'll just show you, like, this is one case, right? When it's, I don't know how many, 1,500 iterations. And you'll see with the other one, how many, like how different it is and how it expands in different ways. Like this one has a larger speed. And I think so like sensor angle and rotation, like rotation angle is different. So it goes more in straight lines. Like the other one would think many times before proceeding forward or left or right, because it had like a larger field of view and like a larger rotation. But this one, you know, just like it senses something in the environment and then it goes. But when it goes, it's more straight. It's like you can see, like in this part, like these lines are more smooth and these lines are more jagged. This is more like in reality, like for example, to have something grow like this, probably in reality would take like a few hours. But this one, for example, you know, it has, yeah, it's like this. And it does not look like the one in reality. So that's why I'm saying, like, not everything in an algorithm is objective. What it's objective is the math behind, but the way we interpret that, it's like the way we make sense of it, it's up to us. And why does it have to be like the same as in reality and like act by the same principles? Maybe we can create or modify it in a way that exceeds reality, you know? I mean, it's also the case that we can modify it in ways that it's dumber than in reality. But again, like even the algorithm, it's even if the most pristine algorithm of slime mold, it is not reality. It's an interpretation of reality, an interpretation of data. Like the slime mold has very many complex things about it, and like all organisms actually. And you cannot like just hard code everything into it and take into account all the things that you know, an algorithm, an organism does. And yeah, so this expands in different ways than the other one. As you can see, like when we grow something, like the algorithm runs a little bit slower. The reason behind it is that it's just it has to do more things. Like for example, if we don't have dynamic population enabled, then it doesn't have to check all the neighbors around it for every particle. So this adds a lot to the complexity or like the number of computations. So it's a little bit slower. And also because of the way it works, it's just that it has like its numbers of it needs larger populations. So like if you want to grow something like the slime mold that we were seeing earlier in the videos from BBC, then you know, you will either need an algorithm on the GPU running, which is quite hard to do in Grasshopper, or you have to wait one night or 24 hours to, you know, to see it, to see the result. But the nice thing about it is that, you know, I mean, I've been a lot of times working with this and other generative algorithms, and it's just a thing that you have to get used to, that you don't get the result instantly. And once you get used to that, it's actually quite fun, because while you're looking at it evolving, you're trying to understand what it does. Something that you wouldn't be able to do if you just had something that would give you the results straight away. So you're trying to predict what it does, and then you get surprised. And then at the end, you have all the frames, you make it up in a video, and then you understand the whole picture. But yeah, I mean, it's just a way of working with things. So this is not parametric architecture, guys. Parametric architecture is just oversimplified geometry. Generative systems are very complex, hard to deal with. But once you get into this, like, you can have access to some kind of logics that are, are more complex and interesting. And also, like, I believe aesthetically, people are starting to get bored. I mean, I got bored of smooth surfaces myself, to be honest. But yeah. Okay, so what I've done here is, like, we have like these two ways of growing. Okay. And now I want to see how these two will interact with each other. So we'll get the third one. And it's almost like they're like two different species here. But it's nice to see the fact that at some point, I mean, they mix with each other, and there are places where one of them tends to stay, and there are places where the two behaviors kind of combine, and they either create something in between or something completely new. So it's quite exciting to, create different, let's say, species and see how they interact with each other and what they do. And at the end of the day, I don't know if they solve a problem from the beginning or they're a solution to a problem, but it's up to us to make sense of that and see how that thing can turn into something useful. So, I mean, for me, for example, one thing that, like, my mind goes to when I see like smoother, larger loops, I think of cars, or like, not necessarily cars, maybe drones that run at a faster speed. And when I see things that are more jagged, it feels like, there are places for things that are moving slower. But my logic cannot, maybe it's not objective, or maybe it's flawed, but it's just the way that I make sense of it sometimes. And it's the same with, like, I know a lot of algorithms. Like, I really, like, I was searching for this thing that, like, having something that's completely objective, but at the end of the day, geometry is objective. Geometry is the only objective thing, and the mathematics behind the algorithm. The rest, it's just up to us. Yeah, it takes some time. Let's see. Okay, let's play a little bit with this. Like for example, if I increase the diffuse range and maybe decrease the diffuse rate, it means that it will release chemo attractors in a more aggressive way, and it will expand further. But if I go back to the initial, another important aspect that I forgot to mention is the decay rate. So like if the decay rate is larger, you will see that it will minimize to the point that it will start losing connections as well, I think. Okay, so this is a dynamic population. You have two different species here that I've started. I mean, I've given you like, because this is not something you find in a book or something that somebody tells you. It's I mean, in my case, when I was writing the algorithm, I just had to find these settings, and by understanding the logics behind and like how these things evolved, and it was maybe faster for me to find them. But you are lucky now that you have like this starting point, and from this on you can like create your own way of dealing with this. Okay, so let's go to the next definition, and I actually let's talk about the elevation map, since we started talking about growth. So I'll drop this in your Dropbox. And I'll get back to the city map at the end. And also we'll have to talk about geometry, so I'll try to move in a little bit faster. Okay, so I'm using an image, and I'm sampling this image as my voxel values. What's happening here? Oh, I think I have something. Okay, so I need to put the birthplace. Oh, okay. So for the elevation map, I will add the Grasshopper file as well. Okay, I have to. Oh, there was a command. Okay, so this will, the algorithm takes a while, but the result is something like this. So we have that picture that becomes an elevation map. And then we have this slime mold that starts somewhere around here. And then it starts populating or like growing in this elevation map. And yeah, this is kind of like the result. It's almost like a parasite. Okay, let me hide this. And this. This is not something that grows in 3D, but that data can be easily transformed into 3D. I showed you. All right. What am I missing? Oh, okay. Make sure that when you open this, you will have the don't draw any preview geometry. So make sure that you turn this on. Okay, so like my elevation map is coming from an image, this image. And this image works with maximum density and minimum density. These are my values. Also, I have, I think one of the species that I just talked about, I think it's the first one. Yeah, the first one that will have the same growth parameters as here. All right. For the image, I'm using the image sampler. When you, I need to send you the image as well, sorry. Okay, so to add the image, you need to go to the address in your folder because I think Grasshopper will save it with my name here. So make sure you get like the right address of your image. Well, let's say this one. And also make sure that the X and Y domain are from 0 to 1. That's quite important. Now with the image, what I'm doing is like, where is it? I'm taking these values that come from the image, and basically black is 0 and white is 1. Okay. And I am remapping these values. So for the maximum density, which means that I'm putting a cap on density, so like on larger than the density cannot be larger than the value that I feed it into that voxel grid. What I'm saying is that in the areas that are very high, like the white ones become the areas that have 0 density, and the black ones that are the valleys, the valley are 1. So I'm mapping this, saying that it can have any value here in the valley, but the more it goes up, the less like the conditions for it to develop are less suitable. So it's in a way like by remapping this, like this is almost like inverting the colors. And I'm also using minimum density, and this minimum density, we can go without it as well. So I'm saying that in these areas that are black, I'm gonna put some minimum density of 0.1. Again, the density comes from 0 to 1. That's the whole domain of density. And it will always keep itself like this. Why? Because when you grow it, it's gonna grow faster if it has some guidelines. And I'm using these black parts as the guidelines of where it should grow. But you will see, I mean, you can see from the result that the density, like this is not necessarily 100% respected. Like if I were to put the minimum density of, I know, 0.5 there, then yeah, I would influence the behavior a lot. But if I put it just 0.1, it will be just a slight hint that those are areas that where it should develop. You can also go without it. It's just going to take a lot longer to develop. And yeah, and it grows and grows and grows. And I don't know if we have time to wait for it to grow, but while we look at it, I'll just explain how I turned this into a 3D geometry. Actually, I'm gonna pause it first. Okay, so again, the beauty of data is that you can grow the whole terrain just based on these values. So again, like white is 1 and black is 0. So the areas which are the darkest, like for example, these ones are lower, and the ones that are lighter are higher. And this is one way of, like, you know, I don't know how the other elevation maps work. I've never used them. I'm like, in my day-to-day, I am more towards the product design. So you can imagine that I didn't interact very much with that. But I'm just saying, like, if we want to emphasize this, I'm just gonna put colors as well on this mesh so you can see. Oh, I'm putting the colors the other way around, sorry. So the black is lower and the white is higher. And what I'm doing here is, like, I have this mesh that I've built, and I'm deconstructing this mesh and keeping the same faces, adding the colors that I want. I can change the colors or keep the same ones actually. And moving these vertices up by these values. These values, for each vertex, you have a value that comes from the data, from here, from the image sampler. If you didn't know about this technique, it can be useful for a lot of other things as well. If you know about it, I'm sorry that I've been boring. Okay. And what I'm doing next to create the rest is basically taking this mesh and deconstructing it. Yeah, I'm deconstructing it into points. But then I also have these values from here. These values, yeah.
And the darker the value, the like, let's just say that oh, actually, wait. So don't take the colors. The values are from voxel densities. So the lighter the color, the higher it is on the elevation. So what I'm saying is like, if there's something that that is light, just raise the already made map, raise by this amount. I can select the amount here. And if I were not to not have colors, like this is the mesh before, again without colors. This is the mesh before adding the values from the slime mold. And it should raise here with the values from the slime mold. And what I did to have this effect of like different colors, just to make, this is just to make it more obvious. I've created the mesh with colors underneath, and I kept the terrain, and that's it. Like, because what happens is, like, if I were just to raise the values from the slime mold, it will be raised flat. But this way, I'm already using the heights that I've gained previously from the terrain, and then I'm raising that. And the thing is, like, it makes sense. I mean, we don't need, like, doing this on a mesh that's like this complex will take much more computational power. I'm not saying it's impossible, but by using this kind of technique, it makes sense logically, because you have, like, it's harder to climb this. So I've made it easier to develop the growth on the river basin, and harder to develop it on the mountain peaks. And yeah, I mean, this is the example with the, I like to call it parasite. And this is kind of the logic. And you have, like, the Grasshopper file, and you can play with it. You can have a look and see what you think. Yeah, that would be nice to have, like, different pets that you put, like, Matthew is asking if I'm interested in any other kinds of organisms for inspiration. I mean, yeah, definitely I will go for the low-hanging fruits, diffusion limited aggregation, agents by themselves. Like, these are a lot more simpler algorithms that I can add, and would be actually interesting to see. Yeah, it could be nice to have, like, a slime mold to interact with diffusion limited aggregation or game of life. Why not? Yeah, this could be things that could be developed in the future, but who knows when. I mean, I'm planning to do it, but I don't know. What are our options instead of putting into a mesh with a gradient? Is there anything way to turn points into curves? Yeah, okay. So we can turn points into curves. Yeah. Yeah, there are a lot of very simple ways to do a lot of stuff. I'll go into geometry a little bit later, because I still have one more exercise to do with you, and then we can all both talk about geometry. The problem is that I haven't prepared, somehow didn't have the time to prepare the geometry files as well, but I will send them to you tonight. I will prepare them I mean, I will do them with you during the lesson, and then I will clean the definition a little bit and send them to you. But yeah, you can turn it into curves, no problem. I mean, you can turn it into a lot of things geometrically, and it all comes back to data. But yeah. Okay, so the next definition is the city map, and I'll just send you the files, and then we'll go through the way I thought about it. But before that, I just wanted to tell you about this place. Snazzy Maps is a place where you can customize your maps and you can explore different styles of maps. I mean, for us, I think the most important thing is to have black and white maps. But what's nice about it is that you can customize the way you see different maps. I don't know why this had this problem. Let's explore another one. So if I want to, like, for example, if I, like, this is the actually part of the map that I've sent you, the Central Park. And for example, if you just want to extract the water, you can give it a certain color, and then you can use Photoshop or whatever to extract it on a different map. By the way, we'll need this as well. So in this map, I'm using like my interest is for the roads, like having the roads for once, so that I can guide the way the particles move around. And also I want to know the places where they shouldn't be going at all, because these are lakes and we don't want to build transport networks on the lake. We should just leave it clear. Or maybe we want, but I'm just, you know, in this exercise we don't. Okay, and did I send you this one? And in this one, we also have an attractor curve. So this will make some people happy. Like I said, like you can develop your own tools that, as long as it's data numbers, you can use whatever, geometry, pictures, and other stuff that you can input into the algorithm. But in a way, it's harder to make, but in other ways, you have more freedom to do the things you want with the algorithm. And I mean, for me, it was more important to have the freedom to do as many things as possible, instead of having the freedom to, or like, I don't know, like just having some predefined things and then just going with those predefined things. Okay, this shouldn't, if I remember correctly, this is not with growth, so this will run faster. And let's talk about the things that are guiding this. Like the complexity you can achieve with the data-driven approach, it's much higher than just having a few attractor points. You can use attractors, you can use BREPs for inclusion or exclusion, maps for, like, you can use pictures for maps. Maybe, I don't know, if you were to do like a really realistic kind of simulation, like in urban design, you might need to use like if you are having problems like I am doing right now with things moving very slow, it's probably because something was enabled. No, it wasn't. It's just taking more time. Okay. So let's see the way we go about it. So we have the, okay. So we have this. We have the first image sampler, again with the image sampler. Don't forget the domain from 0 to 1, and put the image on the path on your computer. And what I'm doing here is like, this is my minimum density, this map. So I'll just show you in a second. So before the particles started moving, this is how my map looks like. By having 0.6 at the minimum density, I kind of constrain the particles to only go on the roads. So like, if we were to, if we want to constrain them to go in certain places, with 0.6 minimum density is good enough. You can also put it like 1 if you just don't want them to go any other place than the roads. But I like to have some bits of jagged interactions with the roads, and like let them have their own kind of brain for a little bit. Second thing that I did, I'm having this map again from 0 to 1, and put the other map, like the one with the water, in the second image, the one that's controlling the maximum density. With maximum density, like I'm saying, like in the black part, X is 0, right? Because these values are, like I was saying, black is considered 0 and white is considered 1. So in the black part, I am if something is on the black part, just put 0, meaning that the maximum density will be 0, no matter how many particles I have, no matter whatever happens, this density will always be kept at 0. And for the white parts, I don't care. So that's why I'm putting -1. -1 means ignore, like ignore the rest of the values. Just don't take them into account. So these are my two maps. I do have an attractor points, and it's previewed like this, like an attractor line, sorry. The reason I did that is because I wanted a little bit of contrast between what happens in the park and what happens on the grid. So you'll see in a moment with the algorithm. And another thing that I did while setting up the positions, like I kept out the starting positions of the particles out of this body of water. After I've done this, I remembered that there's a smaller one here as well, but and here, but yeah, I can do that if you want. Okay. So let's run this. Like, if we look at the particles, you can see that they are moving according to the image. So they are moving on the roads. And this, I was talking about this attractor and what this attractor does. Like, it just increases in this area, it increases the sensor distance and the speed, so that this pattern is very regular and very small, let's say. And I just wanted something like that's yeah, that has like these larger gaps between them. So that was my reason behind. But it's like there's no like actual real reason for that. I just thought that would be nice to have a little bit of a contrast in this. And oh, I do have growth here. Yeah, I don't think growth is gonna help a lot in this one. But yeah, why not? Let's just keep it. I'm saying it won't help a lot because there's just like there are these areas where it can grow a lot. And if we're not careful with the death conditions, we might just kill everything that's here on the grid. But I think I was careful when I was doing this. And yeah, I mean, you can see that, you know, first of all, the particles started everywhere. So the first stage of the algorithm was to minimize its transport networks. And now by increasing the population, it will create some extra paths in between the minimized ones. So that's what the growth does in this case. Another thing is like there are probably very many different kinds of ways of connecting this. And I don't have a hierarchy of like which street is more important than the other. So that's why we have like very many possible solutions. But you know, I mean, it runs on the grid and it keeps everything nice. What I wanted to show you here is like how we can just make the particles not care so much about the grid in some parts. And one way to do that is by in Photoshop. I just want to affect the values a little bit. So if I, for example, do this, like these are places where it will construct its own networks instead of following the grid. So I'm just gonna save this on my computer. And let's see if it updates automatically. Yeah. And if we run the same thing again, these also are very good places to see the difference in what the sensors speed, like what the speed and the sensor distance do. Like it's almost like the scaling of this pattern is so small compared to this. I think actually it might be more interesting like this experiment, because these areas allow the slime mold to grow more freely than the ones with the grid. And if we leave it long enough, we will see like networks connecting it. So yeah, I mean, if a bomb dropped there and someone had to rebuild this like an alien civilization, maybe it would look like this instead of a rectangular grid. Okay, and it runs quite slow because it's adapting the population. But what if I turn off the dynamic population? Will it reach a more interesting result faster? Yeah, I think one problem here, the fact that these are not connecting enough, is that their sensor distance might be too small. If I've increased that a little bit, and you will see that probably the grid will not be respected as much. So we probably had to do like, because the grid is like, you need to put like a small sensor distance and a small speed. Otherwise it will just overwrite the grid like the way it does here in these lower areas. But I feel like, yeah, it's kind of creating better connections now. And it's not even with the dynamic population. So the population is static, the same as from the beginning, just redistributed in the map. Okay, let's see if you guys have any. Well, that's a mean question. It's either you were not paying attention to the logics of the algorithm, or what can I say? This one, which, how is it different from a random crawler? I mean, for some people, it might not be. I don't know, like the whole logics of the algorithm make it like this. So if you re-see the webinar from the beginning, maybe you will find your answer.
Yeah, I don't know if the Libra plugin doing this.
Yeah, but
it's
talking about a random crawler, which means that it's just, yeah.
Just random.
Okay. In the case 3 of the dynamic. So yeah, Matthew, I was saying this before, like sometimes the populations combine and you get like an average, and sometimes you get something that doesn't look like neither of the populations that started from. In the case of dynamic population, when you combine two populations, Matthew was asking what would be the resulting interaction. Most probably it will be average, but yeah, sometimes they can. Okay, agent-based design. Yeah, I mean this agent. Yeah, you can think of these particles as agents, but this is stigmergy-based, meaning that these particles, kind of like the logics behind them are different. So in an agent-based design, the particles don't need a grid theoretically, because they don't deposit values, and the way they interact with each other is not by the values that they deposited on the grid, but rather by their position. So for example, in an agent simulation, you will compute the distance between two agents and see if you have some rules for attraction or repulsion or alignment. So they are similar in some ways, but very different in terms of the results you get from them. But of course, you can get like a hybrid system between the two, and that can also be interesting. You cannot get a hybrid system in Grasshopper the way these things work now, but if someone were to code this, he or she could definitely do it, and get a hybrid between this and others. I mean, you can get a hybrid between many different algorithms. So yeah, but there are different things. You don't need to set a birthplace for the particles. In this last example, you can see that I just put the particles everywhere, and then they just yeah, I mean, you can, like, the in this example, Mădălin, you were asking me if we have to set a birthplace for the particles in the case where we have dynamic population. No, we don't. We can like in this, like I demonstrated in this example, they start from everywhere and they just grow like that. Yes, you can do this in your. You can put other agents to interact with the maps. Adrian, yes, in a way that's true. Like, but it's not necessarily history. It's or maybe it is. Yeah, that's an interesting way of seeing it. But I think you're right. Yeah, I mean, you can also see, like, it's because one of, like, the stigmergy-based models leave trails behind, like chemo-attractor trails, and the agent-based systems usually don't leave any trails. I mean, they leave trails in terms of geometry so that we can interpret that geometry into lines, pipes, whatever. But those trails usually don't mean anything for the agent. So they just interact with their bodies, not with the things that they leave behind. And I think, yeah, history is a good way of saying. You don't have the same behavior on your computer. I think if I run the simulation again, it might have different patterns. So the pattern won't be the exact same one. The characteristics of the pattern will be the same one, Ludovic. But you won't have the same exact pattern, because when the population of particles starts, a random vector that acts as the orientation, the initial one, will always be assigned, I think. And that's why they will always get you slightly different results. But at the end, like the particularities of the pattern are, and the behavior are the same. But you won't get the geometry, like the lines, in the exact same point. Can the slime grow vertically? Yeah, it could. I mean, you can consider this vertical. I don't know what you mean by growing vertically, because it can be interpreted in different ways. But yeah. The promo example files, well, unfortunately, I cannot give them to you because it was like doing them while developing the plugin, and the plugin, like, I've changed components and logics inside, and even if I give you those files, they will either have errors or they will just create different things. So, but I kind of, like, while talking about all the steps, I kind of talked about everything. So you don't need the promo example files. Okay, let's go to the geometry and let's have more questions for later. I'll just go to, I'll just take the behavior. Okay. I'll just make something very simple in terms of like the, so okay, so I want the local angle 60, let's say. I also want this to be like a larger grid is always more fun. The larger it gets, the more complex the behavior and the more interesting the things you get. So you'll see in a moment what I mean. Okay, so I'm just simplifying this file to the point that it's very basic. So the only thing that like from the basic example, I have the angle and I need some settings as well to wrap the values. I mean, you can extract geometry from everything. It's just that in this example, I want to do it like this. The logics are the same. Okay, so forgot about something. So we need the data recorder component. It comes standard from Grasshopper. And I will add it to the particle position. And okay, and it will record all the positions of the particles. You can see like we have like a ton of points. We also have to make some sense out of it. So let's partition this list. Again, like this, in this case, I want to get the trail of the particles. So in order to get the, I'm not using dynamic population. For that one, it's kind of complicated with the trails because particles live and die and they evolve all the time. And yeah, it's kind of hard to organize this data. It can be done. I'm not saying it's not, but it's a bit more complicated.
Madeline, they're asking if you could use the bifocals.
If what?
You can use the bifocals.
Yeah, bifocal. Yeah. Okay, so what I'm doing is like with the data recorder, I'm recording. With the list length, I am seeing like the number of particles so that this data is like split then into like, for example, we have 6 frames and we have 6 lists with the particles. Then I'm flipping the matrix and then we'll have 22,000 whatever number of the number of particles. That's the number of lists with 6 frames each. Okay. I have the wrap in, so sometimes it's not good to have the wrap actually. Okay, so if we just, okay, let me, so this is how you record the places where the particles have been. Actually, this pattern is really nice. I should have used it in the promo. I don't know why I didn't. Okay, so we're creating polylines out of those points. That's one way. We can also custom preview them. So let's say, for example, I want like the trails to have like a certain kind of transparency. So if I want to do that, then I need to know. So I'll need a gradient, and I need to know how many items are in each line, like how many segments each line has. And then I need to make a range, and the domain is going to be from 0 to 1 because we're actually putting it into a gradient. And we should be careful though, because here the number should have x minus 1 because the range splits a domain like anyway, it gives you an extra number, so you don't need it. And this would be the color, and I have my geometry, and I have the made a pattern. Might take a while to preview, but oh yeah, the ones that are at the bottom of the list are red. Actually, you know what? I'll just have to make something with the same color because otherwise it's a little bit confusing. Okay, it's not very nice, but you get the idea. Like if I were to anyway, like this is like the beginning of the list, and this is the end of the list, meaning that this is the most recent one, the black one, and the other one is less recent. if you are rendering this, like if you want to extract a nice image out of this and you are having problems like lines being one on top of the other, you can also move them on top so that you are sure that the line order is good. So you can see like the black one is on top on the gray one. Okay. So this is for making, this is for previewing. The trails. And this is for recording trails. So you see, you can do it by yourself. You don't need a component for that. Okay, another thing that we might want, actually, I'll just remove this from over. Don't worry if you miss some steps. I'm sure some of you are saying that you missed some steps. Don't worry, I'll send you the files. This is let's just use this color for everything that's preview. This makes more sense. Okay, so this is one. What else? We can also preview the particles in other ways. Like, for example, when I'm doing my videos in the promo, you will notice that, like, for example, the white parts are particles previewed differently than what just the pink ones are parts of the density from the grid. So the white ones, to preview them, what I'm doing is, I think, I'm just creating a surface plane and I'm getting this vector. So I can also output the particle angle, and axis, I'll just get the x-axis. No, sorry. So I'll get a vector like this. Hope it's not. Okay, so the way I was doing it, if I remember correctly, yeah, okay, so I have to create a plane with the position of the particle position, the orientation, and the orientation of the vector. If your plane displays very big, like it's very big as mine, you can go here, preview plane size, and make it a lot smaller. And then when creating the plane surface, I'll have this plane, but I also have to get some domains. I'll just write them like this because I'm not constantly gonna play with them. -2, 2. This is for the plane surface. Just to have them like oriented. Of course, in this case, my particles are huge. I'll just lock the solver while I do these changes because it's gonna save some time. And -1, 1. Why I'm doing different values is because I wanna have them oriented. Well, apparently I'm orienting them in the, I think, yeah, this is the right solution. They would go like this. And, you know, you can have geometry preview and color. And if I enable this one, and this also move them up a little bit. Here you go, you have some particles. Like if you don't want to preview those edges, and you want to have transparency, then unfortunately, you'll have to construct a mesh. I mean, Rhino is not like with the preview in Rhino, it's a big problem because it's made to preview actual geometry, and we are trying to make like some transparent things here, and we have to find workarounds. And I think this is enough. Is it transparent though? Is there anything I'm missing? Where is this coming from? Oh, okay. Okay, so when I custom preview the geometry, like this, I can set the level of transparency. So this is for previewing particles. Okay, so since we are at this stage, I can also show you how to make a video. But I will have to disable this because this is gonna take forever, right? So let's call this frames. I'll just make 10 frames now because we don't have a lot of time, but so I'll just add 0 to a number, and every time I add something to, like every time I change something, my algorithm will update. Let's say in this case, let's put this, or no, let's do this. So we have a number that we know, it's 0.1 for diffuse. You see, like I already added something and then the algorithm progressed with 1 frame. So this is my strategy for recording the frames. So I'm just so what happens is, like, this number, no matter how big it is, it will always result in 0 because we're subtracting it from itself. And we are adding 0 to a value that we want to be constant. Of course, if you want to modify the value while the algorithm is running and you're recording things, you can do that as well. Okay, so to record, let's get the frames to 0, and we'll use the record slider. Okay, animate. So right click on the slider, animate. And here, there's this settings tab. Go to top because we want to see the top view. By the way, you'll have this. In order to get rid of this axis, just type grid in the Rhino command and show world axis, no. Okay. Now when we animate, we won't have the problem. Always remember to get the right viewport. And actually the way you see it here, that's how it will record it. You can put the resolution here. In my case, I'll put 500 by 500. And I just want 10 frames. And also I need to say where I want to do it. Test recording on the desktop. So here I set up where I want the frames to be recorded. Here I can set up the name if I want, but frame is good enough. Viewport top to see the view. Resolution 500 by 500 or whatever your resolution is. Usually for Instagram is 1080 by 1080. And then you have the frame count. And you will see here generating frame 1 of 10. And you can see that it's not a very fast process, this recording. But most of the times, like if you need to understand algorithms, it's better to record them than just to see the end result, because you can see what happened in the meantime or how it got to that result. So recording is an important step of the process. And if I go to my test recording, I can see my particle is moving for 10 frames. And then it's up to you to combine these frames in a, I don't know, After Effects, QuickTime, whatever your favorite video composer is. One thing that I should mention is that After Effects doesn't always accept BMPs or like the files from Rhino. So I just got this app, like it's just a Windows app, but I'm sure there's something for Mac as well, called Image Converter, where I add the files and convert them to JPEG before adding them to After Effects, and then I compose them in After Effects. But you can also do that in QuickTime. The problem with QuickTime is that you won't be able to set up the speed and stuff like that. You know, you just have like a basic frame by frame thing, which is good enough to observe the algorithm and everything, but it's worth knowing After Effects. It's like After Effects is like the Photoshop of nowadays, like since most of the content is video. So you have like a ton of tutorials on YouTube. So my advice would be to like Premiere or whatever, like learn one of those. You don't have to learn the whole program. It's just like 5 things, and then you can do decent videos. Yeah. Okay, so let's go on with the geometry. I will unpreview everything because things move a lot faster. Except this, which is by default. And I'll show you when this records enough data. Of course, it's running a little bit slower when it records tens of thousands of points every frame. I just wanted to like become a little bit more simple, and you'll see why in a moment. So what I'm trying to do now is going to be the something similar with the elevation, but I'll show you how I got in these types of geometries. Okay, I think we have enough. Sorry, I was meant to record the voxel densities, not the particle position. Damn, we'll have to do it again. Well, the good news is that I think this will record a little bit faster than points. So I'll just go here. So by clicking X, I just empty the recording list. Otherwise, it will mix the previous values with this. Probably save this as geometry. Yeah, so this runs a little bit faster because the voxel densities are just a number, the particle position are made up of 3 numbers. Okay, this should be good. I do have a question. Does Weaverbird work on Mac? Anyway, I'll just show the. Oh, come on. Yeah, if like I don't press this button, it won't record. Like, I have to do it again. I'll show both ways anyway, because like my preference is to work with meshes than surfaces. Meshes are a lot faster than surfaces. Surfaces are a lot smoother, but even when they're previewed, they're still preview. Like the algorithm for previewing them is still turning them into a mesh before previewing them in Rhino, or when rendering as well. So at the end of the day, you're still working with meshes. So I mean, in this case, I like working with meshes more than with surfaces because it's faster. But I'll show the surface one as well. And yeah, I mean, but I don't know, like if Weaverbird works on a Mac, then you don't need it, but yeah. Okay, let's say this is good. And I want to create a mesh like I'm doing here with the preview, but without any colors. And I'm going to use the densities. I'll do the same thing. I'll partition these lists. Are you for real? I'm recording the particle position again. I can't believe it. Oh. That's what happens when you're in a hurry. Right. What I'm doing is basically, you know, I'm splitting the voxel densities on frames. So I have 70 frames recorded, like 70 lists, and each one has the, you know, the values. And with tree branch, I want to extract different frames. So let's say frame number 11. And what I'm going to do is I am going to take the points this voxel position, and I want to move them we should not forget that the densities are between 0 and 1. So I can just take these numbers and multiply them with something. Let's say 10, 11.20. I didn't even know that this thing existed. So I'm multiplying the, so this is the maximum elevation, and I'm going to move them in Z direction. These are my points, which are moved. And mesh from points. I have it here with the U and V coming from X and Y resolution. And if I unpreview this and preview this in a better way, I was hoping that would look better. Let me just unpreview everything else, because I don't know what's happening here. So my points are these ones. Here I just moved up. And this is my mesh. Okay. Okay, this is how, you can create like a simple mesh. So using those densities as the height. And I'll just go on the top view and I'll keep this separately. And then I'll take, let's take another frame. Like, how many frames do we have? We have 70 frames. Let's pick frame number 60. Okay, so what I want to do is I want to combine both of these. And if I want to combine them in a nice way, what I gotta do is, okay, so if you wanna do surface instead of a mesh, you have the points, you have U, which is X, and you can see that even baking it takes longer, and it's creating some meshes so that it displays it. But basically, this is how you create a surface, and well, it's the same thing. It's nice that you can rebuild it. Anyway, this is the way to create a surface. I'm just gonna stop here with creating a surface because this takes so much time. Okay, good. So what I wanna do is I wanna start using some Weaverbird logics right now. But before doing that, I want to raise this to 40, let's say. So this is very exaggerated. It's like this. And the reason why I'm doing this is because I want to do, so what I want to do is like build some hills on top of, on which to add like the details. So I am going to 20 probably. So I am going to smooth out this mesh here. Yeah, so I want to smooth it. One thing that I want is like here I want it to be fixed so that it doesn't smooth the corners as well. Okay, so you can see that it became a little bit smoother, but still I think it needs around 50 to become even more smooth. Because this is I'm basically varying the height with this simpler pattern and then adding the more complex pattern on top of that height. That's my plan here. All right, just move everything. And I will go back to my other frame. Well, basically I need to copy all of this. Well, maybe not the smoothing part, but copy all of this and redo this step. But with a different frame. So what I'm doing now, oops. I'm deconstructing this mesh and I'm getting its vertices. And I'll lock the solver because it might be a little bit heavy. So I have my vertex position and we said we like frame 11. And I think I moved it around 11. Okay. Let's see what this does. So I basically have this new pattern on top of the other pattern. And then I can construct my mesh back. And I'm going to use the new vertices and the same faces. And here it is. This is the pattern. Of course, we can also make this one a little bit smooth. Maybe 3. Okay, so this is one of the patterns, the geometry. And another technique would be to, I'm actually gonna hide everything. So we can either move the new pattern by moving in the Z direction, or to make it more three-dimensional, we can move it on the mesh normal direction. And that will create a little bit more. Let me see, let me just move them in a way that we can compare. And here, instead of Z, we are going to use the normals. And that should give us some interesting results. Okay, here it's obvious that I've moved it with the amplitude of movement is a little bit too high. But you know, it can be an interesting result, but I'll just keep it around here. And let's say the amplitude of movement is half. Well, this is a little bit better, but still a little bit fat. I'll just do it a little bit smaller. Okay, let's maybe put 2.5, see what happens. Also, I will make this Laplacian smoothing a little bit less because it will smoothen them until we can't see anything. Okay. Let me just check something because I have this feeling that it might be that the normals are not oriented the way I was expecting them to. Oh, sorry about that. And we can always invert the direction. Well, anyway, you get the point. You can play with it. Probably what I needed to do is wait for a pattern that's even more simplistic than this, and then smoothen it a little bit more so that the normals are not like this, like intersecting each other. So like the smoother the surface, the easier it is to put the normals. But this is just another technique, and I really like this pattern. I think it's quite interesting. And and yeah, I mean, we can also like we can do that in Grasshopper as well, but I'm just gonna do it here just to show it quickly. If we want slices, we can always do contour. I mean, this technique is similar to metaballs in the sense that you can think of metaballs as the places where the data has the highest value, and that highest value is raised up like we do here. And then you have like sections which create the surroundings. But this is not like as boring as metaballs. It's actually more directional and a bit more interesting, I would dare to say. But yeah, so I think this is it. I will send this one as soon as I clean this part on the Dropbox. Let's see if we have any other questions. I just did. Like, what do you mean, Giovanni? Like, I just did this earlier. This is how I recorded the videos on Instagram. Well, it depends on what, like Sean is asking, since the geometry is continuously changing, how much time would you consider it is a good amount to generate a sample for analysis? Sean, it's up to you. In this case, I imagine that you would use this mainly for urban development, since paths usually are generated not only.
Hey, Madeline, do you have more exercises, or are we just
No,
doing Q&A? Oh, okay. Do you want to see if anyone wants to ask their question on camera?
Yeah, definitely. Sure.
Okay, so if anyone wants to, just raise your hand with the raise hand button, and we can put your camera on and you can ask your question, or even if you just wanted to discuss something, maybe not necessarily a question. If not, we'll just keep going through these on the list here. No one wants to get on camera? We got one. We got two. Okay, I'll put them on. Okay, so okay, Adrian is joining us in a moment.
Hello, hello.
Hey, Adrian.
Hey, first time doing this. Awesome workshop of what you guys are doing, just to get it on camera. Question, I did post it in the question section as well. Basically, I see using this for urban development because you can trace what you know, pathways. You can trace, because it's way better than an active system where you just go with you know, the, I am so sorry, on camera it sucks. Sorry.
Don't worry about it.
Yeah, I framed it better actually in the discussion. My question is, how would you see, like, how would you use it in other systems, like in real world scenario? Because for urban planning, you see a lot of systems like this being built, but I'm trying to see if I could put this into production somehow. I gave the example for forces in sneakers, for example. If you could simulate forces when walking and use those forces as a pathway, maybe to strengthen
That's a very, very good approach. And a lot of people have been using combining topology optimization and Thesaurus logics. And the reason behind it is that topology optimization, that thing that gives you like the minimal structure that you need. Basically, the logic behind it is that it will create a path for the best flow of energy. And that's it. Like,
but you'd have to apply that in 3D somehow.
Yeah, in 2D, in 3D, whatever, like the concept behind it. And then you have this, you know, the flow of energy where like the forces concentrate. And then the next part where fusarium comes in, like just imagine that, you know, like that density that I was talking about, those values come from a topology optimization. So those are the places where you need material, right? Those are the places where, you know, for sure you need material, and you wanna have the fusarium go there. Also, fusarium is good at creating networks. So you have something that's very good at creating connections, and something that will give you the place where you need to have those connections. So in a way, in product design, I think it's, or building design or whatever, you can use topology optimization with Fusarium. I think it makes sense to use them.
Okay.
And it's one of the things that I'm actually planning to incorporate in the future. But let's see, because both the algorithms are quite expensive in terms of computation. So let's see how I can manage the algorithms so that we can actually get something more than 100 by 100 by 100 boxes. If I don't manage that, I'm not gonna do it, because like this low resolution doesn't make any sense. But
there are already many applications doing that. I mean, you have there are 2 or 3 at least commercial available applications that do that.
But not for topology optimization. I mean topology optimization with Fusarium.
Oh, okay, okay.
Like, no, topology optimization is one of the most used algorithms by engineers and architects, and you have tons of
Yes.
Yes. Already. But one problem for me with topology optimization is that, and you know, all the questions have been like, how can we optimize? How can we solve the problem? But at the end of the day, we just use algorithms for like optimizing something here and something there. Like, where is our brain in all of this? You know, we're just engineers.
I had that debate for a long time, and honestly, I don't think, I mean, I think the computer is going to optimize it, and then it's up to us to make it humane in a way.
It's up to us. Like, the computer only gives you like a hint, and it's up to you how you handle that information, how you make sense of that data. And
but
like,
I don't even think.
Yeah. Go on.
Sorry. My main issue is I don't think the optimization is the issue. More like production limitations. That's the thing I'm facing right now. Basically, because you can't 3D print everything, and you cannot, you know, 5-axis, 6-axis CNC everything. So there's a limitation in production in a way. Or maybe this is going to grow so fast in the next 5 years and you'll be able to use this. Because right now we're still working with 2D in a way.
Yeah, well, the thing is that I always looked at fabrication as being something different. So for example, you know, I'm working with fabrication a lot. And if I were to 3D print something with topology optimization, then I would write a special algorithm that will take into account angles and the fabrication constraints.
Yeah, true.
Otherwise, like, you know, you want to do everything with just some basic Grasshopper tools, and you know, it's something that
not possible.
yeah, I mean, it is, but it's not. You know, it's like people 3D printing
really limited
with 0.4 millimeter nozzles. Like, it's not going to work. It's no efficient. No. But regarding the one thing, like my problem with topology optimization is that, you know, it's been used so many times on so many projects that it's become like almost like Voronoi. It's like when I see it, I'm just scared of it. I feel like I want to run away. It's just so ugly, man. It looks like trees. And I mean, that's my problem. And that's where I think the combination between Fissarium and topology optimization could be interesting, because you will have something that's optimized, but also Fissarium has like this aesthetic expressions. And I've been trying to, you know, talk about this while we like during this webinar. And I think this is an important part that a lot of people don't talk about, because we just say, oh yeah, we're going to optimize this, and that's why we use this algorithm. But I think it's about aesthetics as well, because aesthetics are the most human part of all. The rest is just, you know, you're just clicking some buttons. And at the end of the day, it's like I would use it a lot on aesthetics, and I've used it on 3D printing, and I will use it more on aesthetics, because it can be very expressive. Of course, not in its raw shape, but yeah, I mean, I feel like it's way more expressive than agents, and I've worked with agents for many years. And it's one of the most expressive algorithms actually that I've worked with. So in terms of aesthetics, and for me, like I think 50% of the fascination with it is like 50% is like behavior, seeking the unexpected, and the other 50% is like, you know, when you find something that really works and it also looks good, then you know that you've done it right. And
somebody's gonna build it.
Yeah, I mean, you can be a pessimist like that, or you can build it yourself.
It's on the size, but yes, I agree.
Do you have any other questions?
No, I'd rather let other people ask questions as well. Thank you very much.
Thank you, Adrian. Okay. And let's see here. Change role. Okay, we have another one. From Daruk, which I maybe have mispronounced.
No, that's fine. Thank you guys for the workshop. I'm joining you from Turkey. And well, last year I was doing my thesis in IAC, and I was working on mycelium and the structure, the living structures, and focusing on this kind of algorithms. And last year I started to use Houdini for this kind of stuff, and I found it really rewarding. And I like to ask you if to you, Mădălin, and I think Michael, you also used it from what I can see in Instagram. what do you see? Where do you see in Houdini in this kind of works? I mean, I understand that for example, if you design something for fabrication, the Grasshopper has like obvious advantages. But if it's for you know, working with data or working with behavioral models, I mean, where do you see it, or how do you put it, for example, in the master's degree that you are doing in design morphing?
Okay, so this is like it can be used in definitely for transportation networks. Second of all is like interesting from a growth perspective, like how this thing would develop. So let's say, for example, you have like this human colony on Mars, and we are starting in a terrain that's similar to the one that we've done in the workshop. How would we expand our colony? Because we are the only ones, the first ones that came on that planet. I'm just making this up.
Yeah.
But then how do you take into account the transport networks? Where do you put more emphasis on where the next buildings should be placed and so on? So I think it's all about, I don't know, I like to speculate a lot, and the fact that there's not already like an already done solution, it's because you guys and me as well, we are at the forefront of this kind of thinking with this algorithm. And if we already had the answers for all these questions, then it would be, I mean, I wouldn't be teaching this because it would be too boring. It's been done. So I think that's the nice thing about it, that we have the possibility to think and debate and find ways together to use this and, find practical applications.
Yeah, for me, in the terms of like Houdini or Grasshopper or whatever, it's like, I mean, the algorithm's the algorithm. It doesn't matter where you place the algorithm, as long as you can get the data in and get the result out. If you use the same algorithm in Houdini, you're going to get the same result. I mean, it might be faster or slower depending on what software you put it in, but I mean, like the system is the system. It's not the software isn't determining the system. So like wherever it's easier, I would say wherever it's easier or more comfortable for you to use it, like that's where you should use it.
Oh yeah, I definitely agree. Where I see the thing is where, for example, in EAC, they teach a lot of Grasshopper, and you do everything with Grasshopper, and even the interaction is through Grasshopper to processing. But then the platforms like Houdini are so much better in certain things, and generally the institutes and around that, they're not really exposing you to this how to say, to these different platforms. I mean, do you think because it's,
I think it's because
not popular yet, or?
I just think that like all the software we're using isn't really made for architects. We always, except for Revit, we're just adopting every software. Like even Rhino is not made for kind of this kind of thing. So we're always adopting it, and I think Houdini just like hasn't been adopted yet in such a big way. Like it's like you've been seeing Grasshopper since, I don't know, I've been seeing it in like a really popular way since like 2009, let's say. I'm just starting to see Houdini like more in the past, I would say 2-3 years, you know what I'm saying? So
Yeah.
But definitely like now, like today, more than 2 years ago. Like I saw a few people using it, now I see more and more and more. I'm using it myself. So I think it's just a simple fact that it's just a software that it's not new. Like a lot of people seem to think Houdini is new, but it's actually quite old.
Oh yeah.
But it's just, I think it might even be older than Grasshopper. But
yeah, I think it's definitely older than Grasshopper. Yeah.
but it just wasn't adapted into this kind of work yet. And I think we're going to see a lot more of that happening too. You know, it's happening with like all kinds of softwares like I don't know, like Unreal Engine, this and that. Like it's just like we just keep taking more and more and more, and like the ones that seem beneficial seem to kind of bubble up to the surface and stay there.
About the software talk, I remember I've been using Rhino and Grasshopper for a very long time, like since 2010 or something. But I remember my first interaction with, like, I was at a design morphine workshop, and you guys were teaching like 7 softwares, and there was like a tutor that also knew all of them, and I was like, how is this person even?
Yeah.
You know, how?
Yeah.
How come they are
that was a
good?
fun one, yeah.
But at the end of the day, it's like you know, you have to learn to deal with frustration, because that's what happens at the beginning in the first few steps. You get a little bit frustrated because you're used to a certain workflow, but once you get past that, you know, like having different softwares for different things, it's always a good thing. And I would say, like, you can use Houdini for, I don't know, like particle simulations if it's faster. You can use ZBrush for remeshing. You can use Rhino for, I don't know, like drawings or Grasshopper or whatever. So at the end of the day, they're tools that we use, and it also depends on what you're doing, because if you're a standard architect, probably you don't need Houdini, right? You're not going to model.
Yeah. Because it also comes with a big learning curve, Houdini, you know.
Yeah, it's more of a wall.
Yeah. I mean, bigger learning curve than Grasshopper, in my opinion.
Yeah, I think so too.
Yeah.
Okay, thank you guys.
Thank you.
Thank you.
We have another one. You okay for another one?
Sure. Hello.
Hello.
Hey.
Can you hear me?
We hear you.
Great. I'm loving the workshop, and thank you very much for taking time out of you guys' day to teach this. My question is a little different. I absolutely love all of these things, and I can see all of the different uses in fabrication and in urban design. But my question is, how would you apply the uses of nuclei to countries where they may not necessarily have access to cutting edge technology and 3D fabrication? How would you actually use it in like a country like Angola, where the building technologies are still very basic in a way? What would be the best way to actually use this stuff there?
I think one like, it depends on what you want to do with it. Like one way is to just develop the thinking and like then use the technologies that you have, because at the end of the day, it's a I don't know, it's a behavior that gives you a result, and that you can turn that result in, you know, in anything you want, like in terms of fabrication. So it doesn't have to have the same shape. It can just be like the concept for the way you zone, or the way you, you know, you create a district, for example. You create a new district. and you want to see how the streets are positioned. Like either you have like the best technology or the worst technology, the streets are made the same. Or you can use it maybe digitally in a way that I mean, for me, what's interesting about it is that it's even though it's like a dumb algorithm, it's a reflection of one type of intelligence, and I think that's important. Like, and also, you know, showing other people that there are other types of intelligences out there, like just having conversations with people that can be helpful as well. And I'm actually more towards that at this point with the Thisarium algorithm. Like it's, I mean, for me, it's a tool to develop my thinking and also to see things that I wasn't expecting, or like try things or see other versions of what can be done. So I'm not so, at this point, I'm not so concerned with exactly how this will become physical. It's more like the line of thought that guides the process and the behavior. And then, you know, whatever technology is available, we can adopt it, I think.
I mean, you can even take a kind of manual approach to these things. You know, people are kind of, you know, before complex computing and this, I mean, these kind of things people were solving by hand, mathematically, or you can even solve it with the thing itself, right? Like, you know, this slime mold exists, like the videos you show, and you could set up little scenarios for the actual organism. I mean, it's just like a mold, so it's not like it's an expensive thing, you know. So there's like that kind of, you know, aspect, and you know, the video that Mădălin showed, actually they, you know, all their tests, they were just using the mold. They weren't using any kind of computers or, you know. So there's I mean, it would be quite interesting to design, get your design result just actually using the real thing. I mean, it will take longer, obviously, and might not be as complex so quickly, but you know, it could be really interesting.
And my second question was, how do we take nuclei, or what we can do with it beyond just biomimicry? Because I think that it can be very easy to just try to recreate what biology does in an architecture form, but how can we just go beyond that into something actually very profound? Is it something that is it something that we are still trying to achieve, or is it something that we can actually do? Because what I've seen worldwide from big architects is just they kind of stop at biomimicry, but they don't go beyond that. And how can we do that with this? Is it even possible?
Well, like I was mentioning at the beginning, like this can go beyond the actual slime mold, like because you can, you know, further develop its behaviors and also the conditions in which it is. So some things that are not part of nature. But I believe that the whole point of this from the beginning was to start from something that we find in nature that kind of actually works very well, and take that and then see by different experiments what we can get. Yeah, I mean, I agree with you. Like a lot of architects are, you know, are just stopping at biomimicry. And we can do more than that. I think there are a lot of examples with that, like, but I don't see now at this point with the Nuclei plugin how this can or in which direction it can go. from this point of view.
For me, I think you can use it as a guide. I mean, it's like it could be the same as like the Voronoi problem, right? It's like you can use Voronoi for what it's meant for, which is like spatial organization and alignment, or you can actually display the diagram, right? So in this case, if you consider it as a diagram, if you consider it as just a diagram, right? Like you don't need to display that diagram, but that diagram can inform you of things. Maybe where this flows are more dense, like you need, I don't know if it was a city, maybe that means you need a dense urban center in that area. Where things are more loose, maybe you need like, highway and transport center. So I think it's just up to you to determine it and read it in the way that you need it as a diagram. Like, where the biomimicry comes from is when people just kind of display it for how it looks, display it as the diagram, which if used appropriately in the right context is also like applicable. Like, I think it's very interesting to be, biomimicry if it's something for like a fashion design or an object or a product, but maybe it doesn't need to be so much of the biomimicry if it was for, say, an urban development.
Okay, thanks.
Cool.
Cool, makes sense.
Do you have other questions? Other more?
Oh, no, that was it.
Okay, thank you.
Thank you.
Michael, do we have anyone else?
There's no more.
Okay.
If you want to take a quick loop, I don't know if you want to take a quick loop through if there's any important questions in the Q&A, and if not, we can call it an end. I think a lot of them you answered already. That's why I'm not sure exactly which ones to.
Yeah, I think I kind of answered at least the last one. Yeah.
For that, the nuclei actual building sign besides a wall. I mean, yeah, if you think of it as spatial organization, it's just telling you how to move. You can think of it as a way to move through a space, and that's the interesting thing to me, and that's what you see it doing as a slime mold. In those videos, it's like it's finding a way to move through space without a brain. So,
Yeah.
there is one technical one there. Maybe someone's
Which
having
one?
a problem to match the resolution of the viewport size to the animation, and if you have any advice to solve that.
So you can match it like this, like if I think, yeah. If you want to have like the proportions of the viewport, oh no, this is just this is exactly the viewport. This is the resolution of the viewport, and then from here on, if you want it like twice as large, you can just double these numbers. And was this the question? I'm not sure I'm answering that question.
I think so. Maybe.
Right?
Yeah.
Yeah.
Yeah, they said yes. That was the question.
Yeah, just try different things. So one advice I would say, when you're trying your first animation or your first few animations, just try it with a small frame count. Otherwise, your computer will crash and you might end up losing some important data or like something that you wanted to like really do. So always save before and try it first before actually doing it. And you will, I'm sure you'll get the resolution somehow. I don't know if I answered your question, but it's not hard. You'll find it. you'll find the answer. Just give it a few tries.
Did you answer this one? Can you only set a birthplace for the particles if the model
Yeah.
includes growth? Okay, you did.
Oh, you can set multiple birthplaces, or you can set no birthplace, and you can have it be all over the screen. So it's up to you. I just yeah. I mean, it was just the way it was. The algorithm was done, but in case you're asking whether like you can put the birthplaces, like have like a component with many B-reps, you'll find the answer here in the behavior, and I think this one with the sixth one, where you have these obstacles. Here is like I flip the matrix and so on to get a Boolean and like extract the like multiple places for obstacles if you want to put more obstacles than one. But otherwise, like, yeah, it's just basic Grasshopper operations for the place where you put your particles. Or you can just place them by hand if you if you have the patience.
Okay, well, I think that's about it from what I saw. So yeah, I think that should be it, unless you had something.
Oh, I'm
I would
good.
like to see more of it.
Just wanted to thank everyone for participating in this. I wasn't expecting a big number of people, especially since, you know, it's like such a niche subject, and I actually didn't insist on practical applications that much. So I thank you for this, and I'm hoping that I can develop this plugin further, and that you can comment when I will put it on foot for Rhino, and you can help me guide me towards the place that you think that it should be.
Yeah, don't give it a low rating. By the way, I wore this hat on purpose today because of it looks like the stuff you're doing, the pattern.
Yeah.
Anyway, okay, so end of webinar. In some hours, depends how long Zoom takes to process, you'll get another email on accessing the recording, and also whatever remaining files that Mădălin shares. I think you said you were going to do something there. And make sure to remember to any work that you produce or any screenshots, if you want them to be shared on our Instagram, make sure you tag us at DesignMorphine. And which tag do you prefer, Mădălin, for you?
But my personal one. It's
Personal?
my name, Mădălin _
You want to write it down there or on your screen, maybe? Maybe you can just write it as a scribble in Grasshopper.
Wait, where am I? Sorry, I got lost between two screens.
There you go.
This is
Cool.
it.
Yeah, and of course,
Romanian name.
and of course, Design Morphine, so we can see your stuff and reshare it. And the other thing is, if you have anything you want to be put onto our website from this workshop, any interesting results you get, any screenshots, just send them to results@designmorphine.com.
Here you go.
Perfect. Okay.
Bye, guys.
See you all.